explain the mathematical model, here we have to apply KVL. If we apply KVL, the current through this, let us assume that it is I of t. Therefore, the potential drop across this resistor is R I of t. The potential drop across this inductor is L di by dt. The potential drop across this capacitor is equal to 1 by C integral of I of t dt from minus infinity to t. So these are the potential drops. What is KVL? Algebraic sum of potential drop and EMF equal to 0. The applied voltage is VI of t. Therefore, the algebraic sum of, that is VI of t, applied voltage or EMF, and potential drop are the sum of EMF and potential drops in the circuits are equal to 0. Therefore, Y minus, if we travel along the current direction, there will be a fall in potential. If we travel along the current direction, there will be a fall in potential. If you see, this is the battery, say 5 volt. You are connecting a resistor across this. You know that what is the potential here? 0 volt. 0 volt. What is the potential here? 5 volt. So if we travel in this direction, there will be a fall in potential. That's why minus. So if we travel from A to B, there will be a fall in potential. That's why minus R I of t. If you understand the direction, then only you can put the correct sign. Minus R I of t. Again, we are traveling along the current direction. That's why again minus L di by dt. Again, there is a, we are traveling along the current direction. That's why there is a fall in potential. Therefore, minus 1 by C integral of I of t dt. That's all. Now, equal to 0. Algebraic sum of potential drop and EMF equal to 0. So now, this is an integro differential equation. Integro differential, because it involves both integration and differentiation. If you once take Laplace transform, what you will get is Vi of S equal to, if you bring all this to the right hand side and take Laplace transform, you will get R I of S, assuming 0 initial condition. While taking Laplace transform, let us assume that always in control system, we'll assume that 0 initial conditions plus L S I of S, because for differentiation S, plus 1 by C S I of S, 1 by C S I of S. We are ignoring all initial conditions. If you assume that we are interested in I of t, if we assume that we are interested in I of t, means I of t is the output. We are interested in current through the circuit. Therefore, input is what? The applied voltage VI of S. Therefore, if you find the, if you bring the I of S separately, so outside, you will get I of S R plus LS plus 1 by CS you will get. Or we can write, already I told you that I of S is the output. Therefore, we can write I of S upon VI of S equal to 1 by R plus LS plus 1 by CS. Or if you take 1 by CS outside, you will get CS upon RCS plus LCS square plus 1. So if we put it in convenient form, CS upon LCS square plus RCS plus 1, that is I of S upon VI of S. This form is called, this is also mathematical model. Earlier I said this is the mathematical model. Earlier I said this is the mathematical model. So this is in time domain. This is in frequency domain. There are many advantages writing the system in different frequency domain. One thing is, already I told you that if you inverse time, you will get frequency domain. So because omega is inversely proportional to time, that's why whatever happens at infinite time can be easily found earlier. Whatever happening at infinite time can be found earlier. That is the advantage. One of the major advantage of the frequency domain. There are many advantages that we will see later. But anyhow, this is also a mathematical model. This is also this is also a mathematical model. It is called transfer function. This is called transfer function. What is the definition for transfer function? Transfer function means it is Laplace transform of output upon Laplace transform of input. You see that what we got here? We assumed that I of t is the output. What is the Laplace transform of output? I of s. So this is in the numerator. Denominator, what is that? Laplace transform of input. What is we are giving in the circuit? The input to the circuit is voltage V I of t. That is Laplace transform of V I of t is V I of s. Therefore, the Laplace transform of output upon Laplace transform of input is called transfer function of the system. Transfer function also the mathematical model, but in frequency domain. Or we can say that it is in S domain, or we can say that it is in Laplace domain. It is in Laplace domain, or we can say that it is in frequency domain, or it is in transfer function form. It is in transfer function form. So, what is the definition for transfer function? Transfer function of a system is defined as ratio of Laplace transform of the output to the Laplace transform of the input with zero initial conditions. That is more important. With zero initial conditions. We cannot find transfer function unless it has zero initial conditions. If it has initial conditions, we cannot find transfer function. So, if transfer function is given means we can assume that it is assumed that the initial conditions are zero. Initial conditions are zero. We can immediately understand that the initial conditions are zero. So already this we have seen. Suppose instead of I of t as output, I can assume that the voltage across the capacitor as output. I can assume anything as output. Voltage across the capacitor as output, I want to assume. In that case, what we have to do is, we have to find in terms of, what is the definition for Laplace transform? Laplace transform, what is the definition for transfer function? Definition for transfer function is Laplace transform of output. Since we are assuming that voltage across the capacitor is assumed as output upon V I of s. If we found this, then it is also transfer function. But in this case, what is the output? Voltage across the capacitor is output. Therefore, already we found in terms of I of s. What is the equation? It is we found I of s. Now let us substitute the value of I of s from this equation. We know that Vc of t, voltage across the capacitor, equal to 1 by c integral of I of t dt. Integral of minus infinity to t I of t dt. So if we take Laplace transform of this part, what you will get? Vc of s. We can put V naught of s also. V naught means output. O for output. So we can say either Vc or V naught. Here we are considering it as output. That's why V naught of s equal to 1 by Cs I of s. Substitute in place of I of s. You substitute this. What you will get here is instead of I of s, we can substitute Cs Vc of s or V naught of s. So now we can find V naught of s by we can find V naught of s upon V I of s equal to Cs square upon L. We are taking L outside, S square plus R by L S plus 1 by LC. Why I took L outside? This will be written later. It will be written C by L S square upon S square plus R by L S plus 1 by LC. This form is called pole zero form. I'll explain later. You cannot understand what is pole zero form. Here, what way we wrote another equation I wrote here. I wrote CS upon LCS square plus RCS plus 1. Here, finally, instead of the constant is 1. The constant is 1. All other has coefficients mean that form is called time constant. That form is called time constant form. Here, in this form, the coefficient of S square is unity. The coefficient of S square is unity. The coefficient of S square is unity. If coefficient of S square is unity means this form is called pole zero form. Don't worry, we'll see later. We'll see later. Why it is called time constant form, why it is called pole zero form, that we will see later. So now the transfer function of given electrical system is, transfer function can be called as G of S. Transfer function can be called as G of S. Transfer function can be called as G of S. The output of the system is assumed as V naught of S, that is voltage across the capacitor. What is VI of S? The input voltage applied to the circuit. What is the definition for transfer function? Laplace transform of output upon Laplace transform of input. That we got. That's why this is the transfer function of given circuit. In other words, the mathematical model of the system in Laplace domain, or mathematical model in frequency domain, or we can call it as mathematical model in transfer function form. All are same. We have seen how to obtain mathematical model of electrical system. Now, let us see mathematical model of a mechanical system. This is called the mathematical model of translational system. Mathematical model of a translational mechanical system. Mathematical model of translational mechanical system. In all electrical system, it has the quality of, it has the characteristics of resistance, inductance, and capacitance. A transmission line. The transmission line means where we are getting power, electrical power. It is generated in NLC. Suppose we have only one power station, NLC means definitely it must be from NLC. But here we do not know, because all power generating stations are connected as a grid. That's why we cannot claim that this power is generated from NLC. We cannot. But anyhow, let us assume that the power is coming from NLC only. So it is generated there, and its voltage is raised to 2200 volt. Then it is transmitted from Neyveli to Pondicherry. Here we are getting the power. If you see that it is only wire, you are thinking that it is wire. It has the property of inductance. It has the property of capacitance also. What is the definition for a capacitor? If the conducting medium separated by two conducting mediums are separated by a dielectric medium, two conducting surfaces are two conducting mediums or two conducting surfaces are separated by a dielectric medium, then it is called a capacitor. Two wires are coming, three wires are coming, R, Y, B, three phase. Three wires are different, each has a different voltage with respect to ground. Two conducting surfaces are separated by a dielectric air medium. So it is also a capacitor. Capacitor function also there. Inductor means what? If a coil is in a magnetic field, if a current carrying conductor, automatically it will be in a magnetic field because it induces a magnetic field. That's why it is in magnetic field. So a conducting surface in a magnetic field, then it is called inductance. We can think inductance like that. So there are three wires, R, Y, B. One more is there, that is called neutral. Let us ignore. Three wires are there, R, Y, B. Each has different potential. Each generate a magnetic field. The magnetic field generated by that wire is in that magnetic field, self-magnetic field. Adjacent wire also produce magnetic field. In that, this R wire is in the magnetic field produced by B and Y. That's why it has inductance effect also. Therefore, any electrical system, if we consider, it has the property of resistance, because wire has resistance, you know. It has the resistance property, it has inductance property, it has capacitance property. That's why any electrical system is made up of resistor, inductor, and capacitor. In the same way, any mechanical system has three properties. One is mass, it has the mass. All mechanical system has a mass. Mass means because of gravity, it converted into weight. Mass becomes weight under gravity. So mass. Another property is spring. It is like inductor, or you can say it is like capacitor. Sometimes it looks like inductor, sometimes it looks like capacitor. We'll see later. So a spring effect is there. Suppose a rod is there. If you pull that rod, what will happen to that rod? It will expand, no? If you release, what will happen? It will regain the original shape. So it has the spring property. It has the spring property. It has the dashpot property. In computer center, if you say there is a door closer will be there. Door closer will be there. If you open that, நமக்கு அந்த பழக்கமே கிடையாது. டோர்ல சத்தம் வரும், நம்ம பார்த்து க்ளோஸ் பண்ணணும்ன்றது. One rod is there. One end is fixed, other end you are pulling down and leave it. What will happen? It has the spring effect as well as it goes slowly to that point, or it oscillates and finally settles. Oscillates and finally settles. So that effect is called dashpot effect and spring effect. So any mechanical system, if you model it, it has the property of mass, it has the property of spring, it has the property of dashpot. Does it mean that the mass is attached with a spring, attached with the dashpot? Mass itself has the property. Already for that, I told you that if you take a rod, if you pull that, it has the spring effect. If you leave it, it regains to original position. So all mechanical mass has the three properties. One is mass, the second one is spring effect, the third one is dashpot effect. So similar to electrical system, if you obtain a mathematical model of electrical system, it has resistance, inductance, and capacitance. Like that, if you obtain a mathematical model of a mechanical system, it has three properties. One is mass, spring, and dashpot. First, let us consider the spring. So spring means how we will draw like inductor. So this is spring. One end is fixed, other end is free. If you apply a force here, what will happen? It will elongate. It will elongate because spring will. If you make the force equal to 0, if we make the force equal to 0, then again it will regain to original position. So it means what? If you apply some force, Newton's third law. If you apply a force, there will be equal and opposite reaction force. So spring will generate another force. Because of that, the spring is here. If you apply some force, what will happen? If you apply a force, it will elongate. So it will develop an equal and opposite force. That force is depends upon the displacement. Here, the displacement is x. Displacement, if you displacement is more reaction force will be there. The spring constant is k. The spring constant is k. Therefore, the reaction force by the spring effect is Fk equal to Kx. The force developed by the spring, the opposite force developed by the spring is Kx. If it doesn't generate that force, the spring will move. It doesn't generate that force, opposite force, the spring will move. You understand that? So that the reaction force is Kx. Applied force is F. It must be equal. Otherwise, it will be moving. Otherwise, it will be moving. These two are equal. Therefore, we can obtain a mathematical model F equal to Kx. As far as spring is concerned, we can write the mathematical model. If spring alone is there, let us assume that it doesn't have any mass, it doesn't have any dashpot effect, then the mathematical model of the spring, let us assume that spring doesn't have any mass, zero mass. No ideal spring is there in the world. It has some mass, but let us assume that it has some zero mass. In that case, the mathematical model is F equal to Kx. the stiffness constant, where K is the constant of the spring, its unit is newtons per meter. The displacement is in meter. Therefore, if you multiply these two, you will get Newton, that is the left hand side. If you write any equation, the units must be correct. Whatever the left hand side units must be in the right hand side. That way you can check whether the equation is correct. In lower class you must have studied both side, whether the equation is correct or not, how we can check whether the unit is on both sides correct or not. So here, both sides we have the Newton unit. Therefore, the unit of K is stiffness constant, Newton per meter. One end is fixed. The previous case, what we have seen is one end is fixed. Both ends are free means, what will happen? In this end, I am applying a force of F. This end displaces a distance of x1, and this end is fixed means zero displacement. Therefore, the force developed in the spring is kx1, we can simply write. But this end is moving. This end also moving. A distance of x2 means total deflection depends upon the total elongation. The total elongation is x1 minus x2. Am I correct? X1 minus x2. Therefore, the reaction force is x1 minus x2. K multiplied by x1 minus x2. The reaction force developed in the spring, if both ends are free, is kx1 minus kx2, or K multiplied by x1 minus x2. X1 and x2 are in both same direction. That's why elongation is reduced. Both are in the opposite direction. What is the reaction force? K multiplied by x1 plus x2. Because this end is moving this side, this end is moving to the right hand side. That's why total displacement is x1 plus x2. Therefore, K multiplied by x1 plus x2. Both are in the same direction. Therefore, deflection is reduced. The deflection is proportional to x1 minus x2. That is, deflection is equal to x1 minus x2. Therefore, reaction force is kx1 minus x2. The applied force is F. Therefore, the mathematical model is F equal to K multiplied by x1 minus x2. The second case, dashpot. Dashpot is the basic property of mechanical structure. Basic property of mechanical structure. But this can be understood by this dashpot. Dashpot means, suppose I don't want to, if you leave something, if I leave, it vibrates and then settles, means I don't want to vibrate this. It should go slowly and reach like our door closure. In that case, what they will do, they will put a piston here. They will put a piston here. They will take a piston. This is the piston. Small gap will be there. Here, small gap is there. You can notice that a small gap is there. If this side is filled with liquid, means this cannot move very fast because the liquid has to displace from this side. Because of that, it will be very slow and it will not oscillate. That the behavior is called the dashpot. So this dashpot property also there in the mechanical structure. To write the mathematical model, this will exist only if it is moving. If one end is moving, then only the dashpot property will exist. The door will slowly close. Once it is closed, there is no displacement. Once it is closed, there is no effect, dashpot effect. Therefore, when velocity is there, then only that effect will be there. If you apply some force, the dashpot effect, the force due to dashpot is proportional to the velocity, the displacement, that is dx by dt. It is proportional to applied force. It is proportional to applied force. That reaction force is equal to, proportional to dx by dt, proportional to dx by dt, that is equal to v dx by dt, v dx by dt. So this damper effect or dashpot effect is v dx by dt is proportional to velocity of the mass, If one end is fixed, you are applying a force at one end, other end is fixed, the force applied is F, the displacement is X, the velocity of displacement is dx by dt. In that case, the, the reaction force FB equal to V dx by dt, where B is the dashpot constant. So the mathematical model is F equal to V dx by dt. The dashpot will be drawn like this. Dashpot will be drawn like this, like capacitor. If you draw capacitor in electrical system, how you will draw? Like this. In addition to that, you have to put like this. If you put like this, this is called a dashpot. Sometimes the dashpot also will be written like capacitor. Some books, both are dashpots. How spring is drawn? Spring will be drawn like this. This is not a separate spring. The mass has the property of spring. The mass has the property of dashpot. But this you might have noticed in a DC analog meter. There will be a coil. While drawing the coil in circuit, you will draw this inductance in series with the resistor. You will put. Have you noticed that? There is no resistor separately there. Inside, if you see, one coil will be there. The coil has both the inductance property as well as resistance property. While drawing, while putting the circuit, we are separately mentioning the inductance and resistance. But if you see inside, it will be a single coil only. While representing a motor, DC motor, how it is represented, it has inductance in series with resistance. But if you see the coil, resistance you cannot see separately. The coil has the resistance. That way, in the mechanical system, if you put like this, this mechanical system has mass, it has a spring, it has dashpot meter. It doesn't mean that they are separate. The mass has all these properties. But while drawing, while putting in circuit, illustration, through illustration, if you demonstrate the mass, we put separately, like circuit, that's all. So the applied force is F, the displacement is X, the velocity is derivative of displacement, that is dx by dt, the reaction force is B dx by dt. Therefore, the mathematical model of the dashpot system is F equal to B dx by dt. Here it has no mass, no spring effect, only dashpot effect. The third case is if a dashpot, both ends are free. One end is moving at a has a displacement of x1. Another end has a displacement of x2. So here, what is the velocity of this end? Dx1 by dt. Here, what is the velocity of this end? Dx2 by dt. Therefore, the FB equal to the reaction force, because of the applied force F, the reaction by Newton's third law, the reaction force is FB equal to V dx1 by dt minus same direction. That's why minus V dx2 by dt. Dx2 by dt. So if both ends are free, then the mathematical model is F equal to V dx1 by dt minus dx2 by dt. That's all. It has no mass, it has no spring effect. Suppose the mass has only mass effect, no spring effect, no dashpot effect. Here, if a mass is there, if you apply any force, there will be a inertia. Because of that inertia means mass. Because of that inertia, it generates some opposite force. which is equal to second derivative of displacement, first derivative of velocity or acceleration. The reaction force is equal to acceleration or second derivative of displacement or first derivative of velocity. First derivative of velocity. We can say that reaction force is Fm is proportional to d square x by dt square. Second derivative of displacement, or it is proportional to dv by dt velocity, or simply that is proportional to acceleration. That is proportional to acceleration. Acceleration, how to understand acceleration? If a mass has whether acceleration or not, how to understand? If acceleration is not zero, the mass will move in future. You consider a simple pendulum. If it is vertical, it is moving like this. When it has the maximum velocity, when it is vertical. The string is vertical, it has maximum velocity. It goes. At the end, its velocity becomes zero. Velocity becomes zero. Velocity becomes zero, now it should rest, Why it is coming back again? Because its acceleration is not equal to zero. Its acceleration is not equal to zero. Why acceleration is maximum? What is acceleration? Rate of change of velocity. Earlier it goes this direction. After that it has to come this direction. Direction is changed. That's why velocity is, if we differentiate maximum, direction is changed. That's why velocity, the rate of change of velocity is maximum. Rate of change of velocity is maximum. That's why its acceleration is there, but no velocity. Acceleration is there, but no velocity. That's why it is coming back. That's why it is coming back. So from that, we can understand that if acceleration also zero, then only the mass will become rest. That's why we have to remove the acceleration. We have to remove the acceleration. What we are doing while applying brake on the vehicle, we are removing that force proportional to that acceleration. If mass increases, that energy stored in that mass increases. For example, a cycle is moving at a speed of 4 kilometers per hour or 8 kilometers per hour. Those who are good stamina can pull the cycle and stop. Let us assume that cycle is moving at 4 kilometers per hour. You can pull and stop the cycle. The same velocity bus is moving. Are you able to pull and stop? No. So because you cannot remove the entire energy in the mass. Therefore, the mass has some energy. That energy, if you want to remove, you have to apply brake. That energy is converted into heat. That is different. We don't want to see all those things. So the energy is proportional to mass and acceleration. The energy is proportional to mass and acceleration. The force is equal to mass and acceleration. That mass is constant. So Fm, the reaction force, is equal to mass multiplied by acceleration, or m d square x by dt square. M d square x by dt square. So these two must be equal. These two forces must be equal. That's why it must be equal to F. Therefore, the mass, which has only mass, no spring effect, no dashpot effect, means the mathematical model is F equal to m d square x by dt square. D square x by dt square. If it has all the three properties, then the mathematical model is F equal to m d square x by dt square plus kx plus b dx by dt. If it has all the three properties, then this is the mathematical model. It is identical to electrical system. It is identical to electrical system. It is identical to electrical system. Before obtaining the mathematical model, we have to draw the free body diagram. Free body diagram. We know that if you apply some force, there will be a reaction force. Third law says One is called, because of the mass has spring effect, that's why Fk. It has Fk. It has a dashpot effect, that's why the reaction force is Fb. It has mass, that's why it has Fm. All these three reaction forces, always it will be opposite to the applied force. Always to the applied, opposite to the applied force. The applied force is F of t. Applied force is F of t. And the reaction forces are Fk plus Fb, Fb plus Fm. They are in the opposite direction. That's why I'm writing on the right hand side. Or like KVL, we can say that F of t minus F of k minus F of k minus F of b minus F of m equal to 0. That way also we can write like KVL. So what is free body diagram? If the body is not fixed to any other mass, then it is called free body. If you apply some force, it will move. But if it has a reaction forces and equal to the applied force, then it will be stand still. Now this is a free body. Now this is the free body. In that we are applying a force of F of t. The reaction forces are F of k, F of b, and F of m. That's why this free body remains there. The free body remains there. That's why this diagram is called free body. Free body diagram means we have to take the mass. What are the forces acting on it? If you mark, then it is called free body diagram. Here, this is the mass. This is the mass that we have taken. This is the mass that we have taken, m. It has the property of spring. It has the property of dashpot. If you apply some force, there will be a reaction for m. The force is equal to m d square x by dt square. Because of spring effect, it has k x. Because of dashpot, it has b dx by dt. So these are all marked in the free body diagram. All forces are marked in the free body diagram. So to obtain mathematical model, we have to draw the free body diagram. The forces acting on it has to be marked on that. Then we can write the mathematical model. What is the mathematical model? F of t equal to m d square x by dt square plus b dx by dt plus kx. This is the mathematical model in time domain. The frequency domain we will see in the next class. Mechanical translation systems. To obtain a mathematical model of a given translational system, mechanical translational system. This is the given problem. Given mechanical translational system. We have to draw the free body diagram. Free body diagram. This is the free body. The free body diagram, all the forces acting on it, we have to draw. The first force is the applied force. Applied force is from left to right. Applied force is from left to right. That is marked on the free body. Then what are the reaction forces? Because of this force, the list of reaction forces are, one is because of the spring, Fk. Because of the spring, one Fk. Because of this dashpot, another force, that is Fb. The third one is because of this mass. First, we have to draw the free body diagram. In that free body diagram, that is M is taken, that free body. This is the free body. In that, applied force we have to mark. That is from left to right. Left to right. Then what are the reaction? Because of this force only, there are reaction forces because of spring, dashpot, and mass. The first one is Fk because of spring. The second one is Fb because of dashpot. The third one is because of mass. There is a reaction force M. Here, all the four in the free body diagram, all the forces are marked. F of t is the applied force. Kx is the force because of spring. B dx by dt is the force because of dashpot. Then the reaction force m d square x by dt square because of mass. These are the three reaction forces. The applied force is from left to right. The other reaction forces are from right to left. So, applied force is written on the other side of that equation. The remaining reaction forces are written on the other side. That is m d square x by dt square because of mass, b dx by dt because of dashpot, and third one is kx because of spring. That's all. This is the mathematical model in time domain. How to obtain the mathematical model in frequency domain? We have to take Laplace transform for the given equation. The Laplace transform of f of t is, the Laplace transform of f of t is f of s, and Laplace transform of m d square x by dt square is m second derivative. M second derivative. That's why m s square x of s. The initial condition is s x of 0 minus. So this is, we are assuming that the initial condition is assumed as 0 for transfer function. That's why no need to worry about this. You need not write. This also for second derivative minus dx by dt of x of 0, that is also equal to 0. Then for first derivative b dx by dt, b dx by dt, for that s x of s. Here also again the initial condition equal to 0. Then kx of t is written as kx of s. That's all. So what is the equation in frequency domain? F of s equal to m s square x of s plus bs x of s plus kx of s. If we take x of s outside, you will get m s square plus bs plus k. That is, x of s is the output. That is, what is assumed as output? The displacement of this body. The displacement of this body is, assumed as output. Displacement is assumed as output. That's why we are finding what is the applied force f of t. Because of this f of t, there is a displacement, that is x of t is the output. This is the output. Input is what? Input is that applied force. Therefore, we have to find what is Laplace transfer function. Definition for transfer function is Laplace transform of output upon Laplace transform of input. That is the definition. Here output is the displacement x of s, and the applied force is the input, that is f of s. Therefore, from this equation, we can find x of s upon f of s equal to 1 by m s square plus bs plus k. This is the transfer function of given mechanical translational system. Mechanical translational system. Here, the order of the system is second order. How we are saying that it is second order? Because of this s square in the denominator. S square in the denominator, not in the numerator. S square in the denominator, we can say that it is second order. In other words, from time domain equation also we can say that it is second order, because the main reason is why we are calling it a second order, because of second order differential equation. From that only we are saying that it is second order. This reflects in frequency domain also. That's why we got S square. That's why we got S square in the denominator. It means it is second order differential equation. Now, let us review what are the forces in that mechanical translation system. One is applied force F of t. Applied force, it is in Newton. Then displacement, that is the output. Displacement x of t, that is in meter. Then velocity v, velocity v, that is in meters per second. Then acceleration, another variable. Acceleration is meter per second square. Meter per second square. Then mass. Mass is in kilogram. Mass is in kilogram. And spring stiffness constant. That is Newton per meter. K is the spring stiffness constant. That is Newton per meter unit. Then for dashpot coefficient or viscous friction coefficient, that is called B. Its unit is Newton per meter per second. So this is to review what are the variables and the constants are there in the mechanical system. So for mass, for a mass, what is the reaction force? Reaction force is m d square x by dt square. That is acceleration. Second derivative of displacement is acceleration. Or we can say that first derivative of velocity. Or we can say that acceleration can be said as first derivative of velocity. In velocity form. In acceleration form, F equal to ma. F equal to mass and acceleration. We can say it this way. If you consider a spring, one end is fixed. One end is fixed. You notice that one end is fixed, other end is free. The force is applied at the other end. The spring constant is K. The displacement is X. The velocity is V. The velocity at which it moves because of the force is V. Therefore, the force, reaction force, the reaction force because of applied force F is F of t. The reaction force, but all forces are mentioned here as F. You should understand that this is Fk, Fk. This is Fm. This is Fb. This is Fk. This is Fb. So Fk equal to K integral of V dt. Integral. So velocity, to get displacement, we have to integrate. Suppose we know dx by dt. From that, I want x means what I have to do? I have to integrate. That's all. If you integrate, what you will get? You will get x. Therefore, integral of V dt is the force exerted by this spring, or F equal to kx. The force exerted by spring is kx. If it is dash part, here also one end is fixed. In that case, V dx by dt. If you know the dx by dt as velocity, then bv. Then it is called bv. Similarly, if both the ends are free, then I said x1 minus x2. K x1 minus x2 for spring. If you know, instead of displacement, if you know velocity, integral of v1 minus v2 dt. Both ends are free in the case of dash pot, then v1 minus v2 or v d by dt of x1 minus x2, derivative of displacement, that is velocity. So these are the expressions for reaction force that we should remember to obtain the mathematical model. There is no, these are all empty because there is no acceleration form. Mathematical model of an accelerometer. Accelerometer means, already we have seen pendulum example. In that pendulum, it swings between left and right. When it is vertical, while swinging between left and right, when it is vertical, the velocity will be maximum. If it goes to the rightmost, velocity is 0. If it comes to leftmost, the velocity is 0. But the acceleration is maximum because the velocity is changing its direction. The displacement is changing its direction. That's why acceleration is max. Acceleration is, because of that, it is coming back. Otherwise, it will be there only. Because acceleration is not zero, that's why it's there. So that way we can understand the acceleration. Rate of change of velocity, that is acceleration. This is acceleration meter, accelerometer, to measure the acceleration. It's nothing but a small mass is placed inside, that's all. A small mass is placed inside a box. This is a box. This is a box in which a small mass is placed inside. That's all accelerometer. It has one spring. It has one spring and a dashpot. The mass has the property, or if the property of the spring, the property of mass has zero spring constant, 0b means we can attach additional. Like that you can imagine. So it has one mass, one spring and a dashpot it has. That's all. That's all about accelerometer. I want to measure the acceleration of your body. With that body, it is attached. That's why this line, these lines are, it is attached to a mass of which we have to find the acceleration. That's all. Here, it is attached to a mass whose acceleration has to be found. Its displacement is x. It is attached to this a car, let us assume. The displacement of that car is x. Now we have to find the acceleration of that car. The acceleration of the car can be found from this y. This y is the displacement of this mass. Because this mass is loosely fitted. One side is spring, another side dashpot. It is loosely fitted. It is not rigidly fitted to the mass box. It is loosely fitted to the box. That's why it can move. It can move. The displacement is y. Now we will write the mathematical model. From that, we can understand what is the acceleration. What are the reaction forces here? Reaction forces are Fm, Fb, and Fk. There is no applied force, that's why 0. No applied force. F of t, applied force equal to 0. That's why the right hand side is 0. Left hand side, M. The reaction force because of mass. The reaction force because of dashpot. The reaction force because of spring. What is the reaction force because of mass? M multiplied by d square, the displacement, by dt square. What is the displacement of this mass M? It is loosely fitted. If you travel in bus, if bus starts, you are standing on the bus, not sitting. Which side you are moving? Opposite side you will move in the opposite. Bus is moving to the left means you will move in the right. That's why this y direction is mentioned in the opposite direction. So net result, both are in the opposite direction. Same direction means we subtracted. Same direction means subtracted, but it is in the opposite direction. That's why it should be, what is the net displacement of this M? X minus y or x plus y. For spring and dashpot, we have seen that if the same direction, the deflection is x1 minus x2. We have seen, you know. For dashpot also, the displacement is x1 minus x2. But here we wrote y1 minus y minus x. Why? You see that the box is moving this direction. This mass, this M also move in this direction. How much? X direction. This is attached to that mass. At the same time, this mass moves to the right, as we mentioned, it moves to the right by a displacement of y. Now, what is the net displacement of the mass? X is moved this much. This end to this end it is moved. But because of y, it comes little bit less. What is the total displacement from this one to this one only? Can you understand this point? Not like spring. If it is spring means both are moving in the same direction. Means this is you notice that here the spring is moved to this point. Now x1, x2 is come closer. That's why the net displacement is x1 minus x2. Here the mass is moved from this point to this point. The entire box is moved. We should not say mass. The entire box is moved from this point to this point, say x. In that, the mass is little bit came this side because of acceleration. That is y. Therefore, xy, y minus x. X minus y or y minus x? We are considering y as positive. From the diagram, we can understand that y is positive. That's why y minus x. So y minus x. M d square y minus x by dt square plus b dy by dt. As far as spring is concerned, one end is fixed, the other end is displacement of the mass by y. Therefore, for the dash part, the displacement is only y. Therefore, b dy by dt. Only y. No x displacement for the dash part. How the dash part moves, how much? Suppose the mass is not moving. What is the displacement the dash part? 0. But it moves a displacement of y. That's why b dy by dt. The spring displacement is only ky. As far as mass is concerned, the mass in the space, the free body, how much it moves is important to find the acceleration. That's why it is y minus x, not for spring and dash part. That's all. Now you can write this x is negative. That's why you can bring this x to the other side. Therefore, m d square y by dt square plus b dy by dt plus ky equal to m d square x by dt square. But we know that we have to find the acceleration of the car in which the box is attached. That is, the car displacement is x. We are going to find the acceleration of a car. Its displacement is x. So what is the acceleration of the car? D square x by dt square. Therefore, we are interested in m, not m. We are interested in d square x by dt square. We have to find the acceleration because it is an accelerometer. We have to measure the acceleration. So ma, we can simply put ma. Here, m d square y by dt square b dy by dt plus ky equal to m d square x by dt square. For constant acceleration, the change in acceleration, second derivative of acceleration is 0. The first derivative of acceleration is constant, 0. In that case, we can assume that d square y by dt square and dy by dt are 0. If you assume like that, only ky is there. Therefore, ma equal to ky or a equal to k by m multiplied by y. K by m multiplied y. Therefore, constant acceleration is equal to k by m multiplied by y. If you know y, you can find the acceleration. Constant acceleration. What is constant acceleration? If acceleration is constant, there is no change in velocity. It remains constant. Acceleration is constant means d square y by dt is 0. Why d square y by dt square? Y is a function of acceleration. There is no change in acceleration. That's why d square y by dt square is 0. Similarly, dy by dt, that is also a function of y. Y is function of acceleration. There is no change in acceleration. That's why dy by dt also 0. So for a constant acceleration, the equation can be reduced to ky equal to m d square x by dt square. But d square x by dt square is acceleration. We can replace d square x by dt square as acceleration. Therefore, ky equal to ma or a equal to k by my. That's all. This is for constant acceleration. For the acceleration is not constant means, then it is called dynamic equation. Then it is called dynamic equation. In that case, what happens to the transfer function that we will see now? S square y of s. I am taking Laplace transform. B y of s plus k y of s equal to a of s. A of s. Acceleration. D square x by dt square can be assumed as acceleration. A of s. What is the output? Acceleration is the output. What is the input? Input is displacement, y. Therefore, we can find, sorry, I said in the other way. Y is the output. Acceleration is the input. For accelerometer, what is the input? Acceleration is the input. What it gives, the measurement of acceleration in terms of y it is giving. For that, the scale must be in acceleration scale. The scale must be in acceleration scale. In a voltmeter, inside the voltmeter, it deflects. Deflection type voltmeter you might have seen. Actually, what it gives, a force is developed, the needle is deflecting. But what is in the scale? It is in voltage. It measures like that. The scale is in acceleration. Therefore, y is in acceleration. Therefore, y is the output. Y is the output. Acceleration is the input. Therefore, the transfer function is y of s upon a of s equal to m upon s square plus b plus k. That's all. This is a dynamic equation. This is dynamic equation. This is dynamic equation. Here, acceleration is not constant. Acceleration is not constant. The acceleration is varying. Then the mathematical model is y of s upon a of s equal to m upon s square plus bs plus k. Bs plus k. This is second order equation. What is the form? Pole zero form. Pole zero form. Instead of k, if you divide the equation numerator denominator by k, it is time constant form. Here, if m equal to 1, then it is pole zero form. For that, what we have to do? We have to divide by m by m, s square plus b by m, s plus k by m. This is in pole zero form. ms square plus bs plus k, neither in the pole zero form nor in the time constant form. It is in, now if you write in terms of s square, then it is in pole zero form. Mechanical rotational system. So far we have seen mechanical translational system. Mechanical translational system. Now rotational system. Translation, linear displacement, x. Rotational system means theta. It rotates. The displacement is theta. Mechanical rotational system. Here, the application is not force, torque. The application is the input energy is torque, not force. Input energy is torque. The applied energy is torque. The displacement in the spring is theta. The displacement in the spring is theta. One end is fixed. Because of the torque, the applied torque, the displacement in the spring is theta. Therefore, the reactional force is k theta. Reactional force is k theta. Applied energy is, the reactional torque is, not reaction force, sorry. The reactional torque is k theta. Applied torque is T. Therefore, these two must be equal by Newton's law. Therefore, T equal to k theta. That is the mathematical model. Here, mass equal to 0, dashpot, no dashpot effect. Mass is 0. Therefore, the mathematical model equal to k theta, t equal to k theta. That's all. If both ends are free, then that is t equal to k multiplied by theta 1 minus theta 2. Both ends are free. This displays by an angle theta 1. This is followed but by theta 2 only. Therefore, net displacement in the spring, rotational displacement is net angle, angular displacement is theta 1 minus theta 2. Therefore, t equal to k multiplied by theta 1 minus theta 2. This is rotational system. In the same way, dashpot effect. The angle is theta. Angular displacement is theta. Angular displacement is theta. The applied torque is T. Applied torque is T. Dashpot constant is B. Therefore, applied torque must be equal to TB. That is equal to B d theta by dt. That's all. B d theta by dt. But d theta by dt is angular velocity omega. That's why we can write B omega also. B omega also. If both ends are free, one end has a displacement of theta 1, other end has a displacement of theta 2. The dashpot constant is B. Therefore, B d theta 1 by dt minus d theta 2 by dt. Why theta 1 is taken as positive? Because theta 1 is in the end in which torque is applied. The end in which torque is applied. The other end has to be taken as negative. The applied torque side must be taken as positive. Therefore, theta 1 minus theta 2. If it is both ends are free, the mathematical model is torque equal to B d theta 1 by dt minus d theta 2 by dt, or B multiplied by omega 1 minus omega 2. That's all. One more that is missing. That is, it has inertia. It has an inertia J. Applied torque is T. Displacement is theta. Displacement is theta. There, mass M. Here, moment of inertia J. Moment of inertia J is a constant. Because of mass only, it is constant. Therefore, it doesn't have any spring effect. It doesn't have any dashpot effect. In that case, the applied torque is as a reactional torque of J d square theta by dt square. D square theta by dt square. Or J, if you know the velocity, d omega by dt. Or J angular acceleration, alpha. The or you can write J alpha. If both ends are free, that inertia, both ends are free. This end we applied a torque T. This end has a displacement of theta 1. This end has a displacement of theta 2. In that case, the mathematical model is T equal to J d square theta 1 by dt square minus d square theta 2 by dt square. Or this can also be written as J d omega 1 by dt minus d omega 2 by dt. Or which can also be written as, which can also be written as J alpha 1 minus alpha 2. That's all. This is for rotational system. What are the constants and variables in that rotational system? Torque, the applied energy, is in the form of torque. Its unit is Newton meter. Torque is what? Suppose this is subjected to a torque of T, means the force is applied at this point. Linear force F is applied here. This is the distance x. Therefore, T equal to the torque equal to Fx. That's why the unit is Newton meter. Angular displacement is theta radians. Angular displacement is theta radians. Angular velocity is omega t radians per second. Angular acceleration is radians per second square. Linear means here what we will say meter. Linear means here meter per second. Linear means meter per second square acceleration. Here radians per second square. The moment of inertia J, the unit is kg meter square. Kg meter square. The stiffness constant of the spring K is Newton meter per second per radian. Newton meter per radian. And the damping torque is, that is B, is Newton meter per radian per second. Per radian per second. That's all. So these are the, we should know the units as well as the variables and the constants used in the rotational system that we have seen. Here also we have to draw the free body diagram. What are the applied torques? We should mention. What are the reaction torques? We have to mention. Then by using law of motion, we have to write the equation. Here, one end is fixed. Therefore, T equal to the applied torque equal to the reactional torque equal to J d square theta by dt square. J d square theta by dt square. If it is a dash part, one end is fixed. In that case, B d theta by dt. Or B omega. J d omega by dt. For mass, one end fixed. The diagram is wrong. If it is spring, it is k theta. If you know the velocity, angular velocity, if you know, that is k integral of omega dt. If both ends are free, means in the case of dash part, omega 1, b omega 1 minus omega 2, or b d theta 1 minus d theta 2 by dt. In the case of spring with both ends are free, means k theta 1 minus theta 2. If you know the velocity, integral of omega 1 minus omega 2. That's all. So these are all we should remember to obtain the mathematical model. Rotational system, we have to obtain the mathematical model. This is the given rotational system. This is the given rotational system. The applied torque is, this is some problem in rotational system. So this is the torque applied. One end is fixed. One end is fixed. Torque applied is T. The displacement, one end only. Other end is fixed. That is theta. The spring constant is K. The spring constant is K. Dashpot constant is B. The moment of inertia is J. This should be here. We can write the mathematical model. If you draw the free body diagram, J, the applied torque is T. Because of that, the end has a displacement of theta. The reactional torques are Tk, Tb, Tj. Tk is equal to what? K theta. Tb equal to V d theta by dt. Tj equal to J d square theta by dt square. So if you substitute these values, we'll get T equal to J d square theta by dt square plus B d theta by dt plus K theta. This is the mathematical model in time domain. To obtain mathematical model in frequency domain, we have to take Laplace transform. Laplace transform of this variable. T is variable, applied torque is variable, T of S, that's all. We do not know the form of input. Torque, that's all. So we have to write T of S. If you write Laplace transform of this J d square theta by dt square, assuming zero initial condition, J S square theta of S. B d theta by theta. If you write the Laplace transform, assuming zero initial condition, B S d theta of S. K theta, if you write K theta of S. Theta is the output. Displacement is the output. Displacement is the output. So we have to find theta of S upon the input T of S. So take theta S outside, what you will get? Theta of S outside, if you take Js square plus Bs plus K. Therefore, theta of S upon T of S, the transfer function is output. Laplace transform of output by Laplace transform of input is 1 upon Js square plus Bs plus K. Js square plus Bs plus K. This is second order differential equation. Second order differential equation. Write the differential equations governing the mechanical system shown in figure. There are three masses are there. M1, M2 and M3 are the three masses. They are connected through the springs K1, K2, K3 as well as B1 and B2. The force is applied at M1. Now we have to obtain the mathematical model in time domain. That's differential equations we have to write. First consider M1. First consider M1. What are the forces acting in? The applied force F of T is acting on it. And what are the reaction forces? The reaction forces because of mass is M1 d. What is the displacement? X1. D square X1 by upon dt square. What are the other forces? Because of spring K1. K1, other end of the spring is fixed. That's why K1 multiplied by X1. Because of B1. B1 multiplied by dx1 upon dt. One more reaction force because of the spring K2. Because of that K2, both ends are free. Both ends are free. The K2 is connected between M1 and M2. K2 is connected between M1 and M2. That's why both ends are free. Displacement at this end is X1. Displacement at this end is X2. Therefore, because of this K2, K2 multiplied by x1 minus x2. Both ends are free means and displacement direction is same. That's why x1 minus x2. That's all. Therefore, the first mathematical equation for the mass m1 is f of t applied force equal to m1 d square x1 by dt square plus b1 dx1 by dt plus k1 x1 plus k2 x1 minus x2. That's all. The first equation is over. Why we wrote f of t one side and all other forces on the reaction forces on the other side, they are in opposite direction. F of t is downward, all other reaction forces are definitely upward. So that's all. The displacement in this mass is x1. Now, if you take the free body diagram for M2, the free body diagram for M2, what are the forces? No applied force on M2, but only reaction force. What is the direction of displacement? Direction of displacement is downward. Therefore, reaction forces will act upward. What are the reaction forces? M2 d square x2 by dt square plus spring K2 is connected, but it is connected both the M2 as well as M1. Therefore, K2 multiplied by x2 minus x1 because x2 is reference. Earlier, how we wrote x1 minus x2 while considering M1. But here, while considering M2, we have to write x2 minus x1 because the direction x2 is considered. Therefore, x2 minus x1 plus that is the only difference. Then K3 is connected here. K3 is connected here. K3 is connected here. Therefore, the reaction force because of K3 is K3 multiplied by x2 minus x3 because both ends are free. Similarly, B2 also connected. B2 also connected. Therefore, because of B2, the force acting on it, reaction force acting on it is B2 multiplied by x2 derivative of x2 minus x3. x2 minus x3. That's all. Therefore, the equation for second mass is 0 equal to, because no applied force, 0 equal to m2 d square x2 by dt square plus b2 d upon dt of x2 minus x3 plus K2 multiplied by x2 minus x1 plus K3 multiplied by x2 minus x3. That's all. For second mass. Third mass, what are the reaction forces acting on the third mass? The reaction forces acting on the third mass, no applied force, only reaction. Displacement is downwards. Therefore, the reaction forces are acting upward. The first reaction force is Fm3. The second reaction force is Fk3 and Fb2 are the three reaction forces acting on it. What is the equation? 0 equal to m3 multiplied by d square x3 by dt square plus K3 is connected both M3 and M2. Here X3 is considered as X3 displacement is considered as far as M3 is considered. Therefore, for this dashpot B2 multiplied by d by dt of x3 minus x2 plus K3 multiplied by x3 minus x2. That's all. So these are the three differential equations governing the given system. For one system, there are three differential equations. Three differential equations. So how many differential equations will be there? Number of differential equations equal to number of masses. Number of differential equations equal to number of masses. That's all. So if it is the electrical system, number of differential equations equal to number of loops. If it is KVL. If it is KCL, number of differential equations equal to number of nodes minus 1. Because one node will be taken as a reference. So while writing KCL, you will find the number of nodes. Now after finding number of nodes, what you will do? One node will be taken as a reference. For remaining nodes, you will write KCL. Therefore, number of equations for KCL, current equation. Kirchhoff's current law, if you write number of equations equal to number of nodes minus 1. If it is KVL, Kirchhoff's voltage law means number of equations equal to number of loops in that circuit, number of loops in that circuit, number of closed paths in that loop. As far as mechanical system is concerned, number of equations equal to number of masses. M1, M2, M3, 3 masses are there. Therefore, 3 equations. That's all. So these 3 differential equations together represent the given mechanical system. Together represent the mechanical system. That's all. As far as this question is considered, what is the question? Write differential equations governing the mechanical system. That's all. So answer is over. You have to draw the free body diagram. You have to mention all the forces acting on it, applied forces as well as reaction forces. Then you have to write the equations. That's all. This is for electrical system. As far as the electrical system is concerned, if it is a resistor, we can write the equation for voltage across the resistor. What is the voltage across the resistor? I multiplied by R. R is constant, I is variable. So current through this resistor is voltage across the resistor. Voltage across the resistor VR equal to voltage across the resistor equal to Ri. What is the current through the resistor? I equal to, what is voltage across the resistor? V divided by R. That is current through the resistor. If you write expression for current, V by R. If you write expression for voltage, IR, you can write the expression in terms of charge also. What is the definition for current? Rate of change of current. Rate of change of current. The velocity of electron is current. Actually, the velocity of electron is considered as current. Current itself is dynamics. Current means dynamics. So that is velocity, dq by dt. Rate of change of charge in a circuit is current. Therefore, instead of current, we can put dq by dt also. Therefore, voltage across the resistor equal to R dq by dt. dq by dt. If it is an inductor, what is the voltage across the inductor? L di by dt. The current through the inductor is I. Voltage across the inductor is V. In that case, V equal to L di by dt. What is current through the inductor? 1 by L, 1 upon L, integral of V dt. We have to integrate the voltage. If you consider current I equal to dq by dt, then di by dt becomes what? I equal to dq by dt. What is the derivative of current? T square q by dt square. Therefore, we can write voltage across the inductor can be written as L t square q by dt square, because I equal to dq by dt. If we differentiate, therefore, di by dt equal to t square q by dt square. That is substituted here. In the case of capacitor, what is voltage across the capacitor? V equal to 1 upon C integral of I dt. Integral of I dt. What is I? Current through the capacitor. I equal to C rate of change of voltage. C dV by dt. But I equal to dV by dt. I equal to dq by dt. dq by dt. Therefore, if you integrate on both sides, di dt, integrate on both sides, integral of dq by dt multiplied by dt. Integrate on both sides with respect to time. You will get dt getting cancelled. Therefore, you will get Q. Q equal to integral of I dt. Integral of I dt. Q equal to integral of I dt. Because I equal to dq by dt. Therefore, integral of I dt equal to Q. Here, integral of I dt is there. So we can replace this integral of I dt by Q. Therefore, V equal to Q upon C. V equal to Q upon C. We can replace integral of I dt by Q. Therefore, V equal to Q by C. Why all these equations? Why the up to second column already you have seen? Why all these, this fourth column? Why? That we are going to see now. Before seeing that, what is out of these four equations, which is familiar with you? V equal to 1 by C integral of I dt. Am I correct or not? Most of the times you used this 1 by C integral of I dt equal to VC, voltage across the capacitor. So if you remember this only, all the remaining four you can easily remember. So what is VC equal to 1 by C integral of I dt means? These two are if you write for VC, if it is integrator, you have to write for IL. Instead of 1 by C, 1 by L. VDT. So instead of I, V, VDT. That way you can remember for integrator. If you remember for capacitor, you can easily remember for integrator. The opposite way. Replace V by I. That's all. Replace I by V. You can easily remember. And we know that this also you can easily get. If you differentiate on both sides, what you will get? So you can easily remember this. So from that you can identify this. Replace I, V by I, 1 by C by 1 by L, I dt by V dt. That's all you can easily remember. If you differentiate on both sides, what you will get? This equation. C dV by dt you will get. If you differentiate on both sides, you will get dV by dt. Here you will get I. If you bring that C here, you can get this. So in the same way, you can remember this. Replace I by V, C by L. That way you can remember. So if you remember this one formula, you can get all other three. But these three are important. Why? That we will see now. Analogous systems. For a mechanical system, we can find an electrical analogous system. Electrical analogous system means the differential equation governing the systems for electrical as well as mechanical are identical. What is the mathematical model of this given mechanical system? What is the mathematical model of this given mechanical system? Displacement, the applied force is F of t, the displacement is x, the velocity is v. Therefore, the mathematical model is F of t equal to, because of mass m, d square x by dt square. Because of this b, you can write b dx by dt. Because of this k, you can write kx. That's all. This is the mathematical model in time domain. What is the mathematical model of this electrical system? The electrical system is V of t equal to V of t. The applied voltage is V of t equal to the current through this circuit is I. If you write KVL, what you will get? Ri, the drop across. If you travel along the current direction, if it is a battery, you are traveling from negative terminal to positive terminal. That's why this is positive. V of t, you can write positive. Why positive? You are traveling from negative terminal to positive terminal. If you travel along current direction, you would put minus Ri minus L di by dt, because the potential drop across inductor is L di by dt. What is the drop across C? Minus 1 by C upon 1 upon C integral of I dt. If you bring all these to the right hand side, you will get this equation. So this is the mathematical model of the given electrical circuit. If you write in terms of charge, what you will get is, if you write in terms of charge, you will get V of t equal to I L di by dt. We know that I equal to dq by dt. Therefore, L d square q by dt square. This is replaced by L d square q by dt square. We are writing in terms of q, not I. I is dq by dt, that we know. Therefore, this Ri becomes R dq by dt. I equal to what? Di by dq by dt. If you replace I by dq by dt, dt getting cancelled, integral of dq is q, therefore q by c you will get. We are writing in terms of q, in terms of charge, that's all. If you see this equation, say A. If you see A and B, if you see A and B, B is differential equation governing mechanical system. A is differential equation governing electrical system. If you see here f of t, here f of t, here v of t, here v of t, here m d square x by dt square, here L d square q by dt square, here b dx by dt, here r dq by dt, here kx, here 1 upon c q. Both equations are identical, not equal. Identical equations are there. If L equal to m, R equal to b, if L equal to m, R equal to b, and 1 by c equal to k, both systems are analogous systems. Which is simple. Construct. Suppose you want to construct a system, you will be given RLC. You are given spring, dashpot, and mass m. Which is easy to construct? Electrical or mechanical? Mechanical. Electrical or mechanical? This is simple system. That's why you said mechanical. Mechanical system, how you will connect K? One end should be fixed end. Other end should be connected to mass M. Is it simple to connect mass and another end is fixed place you have to connect? Similarly, dashpot has to be connected. You have to weld it. If it is electrical system, how you will connect the resistor and inductor? Just twist, that's all. Simply you can construct. So, if R, L, C, resistor, inductor, and capacitors are given, which system can be easily constructed? Electrical system, not mechanical system. Constructing mechanical system is difficult. This is simple system. That's why you say mechanical system is simple. Electrical system, just connect R, L, C and connect a battery. That's all. Which is easy. Since you are a circuit branch students, you must have said electrical system than mechanical. If you want to connect a spring with the mass, how you will connect it? You have to weld. Or some means you have to connect. If you use a screw, what will happen? There will be change in mass. The electrical system also there will be a change because of connection, but if it is negligible, then okay. Anyhow, constructing the electrical system is simple. Constructing electrical system is simple. Suppose this system, which is simple, electrical or mechanical? Definitely electrical system. So, for any complex system, we can easily get a electrical system. Therefore, instead of doing experiment on mechanical system, we can do the same experiment on electrical system. We can find the output. Suppose you designed a mechanical system. For that, you want to check practically, but very complex system. Very complex system. Conducting experiment on this very difficult. So construct the electrical system and do the simulation. But nowadays you have computer simulation. That's why it appears simple. It appears simple, computer simulation. But those days before inventing computers, how they simulated mechanical system by electrical system. So they need the analogous systems. So any mechanical system can be converted into electrical system, analogous electrical system, so that they can simulate and find the output without conducting mechanical experiment. Without conducting mechanical experiment. Similarly, if it is a biological system, for that you have the set of differential equations. For that you can construct a electrical system, you can conduct the same experiment electrically. You can conduct the same experiment, you can find the output. Instead of X, you will get Q out. Q is there. X there, displacement is X there. What is the equivalent variable here? Q. You have to find the Q. If you know I, from that you can find Q. If you know the I, you can find Q. That is the only difference. So finding analogous electrical system for a given mechanical system is important. So now let us find the analogous electrical system for a given mechanical system. Before going that, how you can get a mechanical system, electrical analogous system for a given mechanical system. Replace M by L. Replace B by R. Replace K by 1 upon C. That's all. You will get, you find the L, which is equivalent to M. You find the R, which is equal to B. You find the 1 by C, which is equal to 1 by K. Find a C, which is equivalent to 1 by K. So you have to find the inductor whose value must be equal to M. You have to find a resistor whose value must be equal to B. You have to find a capacitor C, its value must be equal to 1 upon K. That's all. You can construct a electrical system. So now what are the equivalences? For a given force, the equivalent analogous electrical system, voltage V. For velocity, dx by dt. Velocity means dx by dt. Here current. Here mass M means here inductor L. Here viscous friction coefficient B means here R, resistance. Here displacement X means here charge Q. Here stiffness constant K means 1 by upon C. Therefore, C equal to 1 by K. To find C, we have to find 1 by K. That's all. You will get electrical equivalent circuit. Now let us find the electrical equivalent. Already we found the electrical equivalent circuit for this system. This is the mechanical system. For this identical analogous electrical system is this. One inductor, one resistor, one capacitor. That's all. If you put all these things, you will get this electrical analogous system. That's all. All connected in series. Only one loop. How many equations are there? How many mechanical equations are there? One. Therefore, in the electrical system, one loop will be there. So all are in series. That's all. All are in series. But here, how many equations are there? 3 equations are there. 3 equations are there. Therefore, 3 loops will be there. In the electrical system, how many loops will be there? 3 loops will be there. We'll draw that circuit now. 3 loops will be there. The first loop, what and all there? F of t. That is V of t. Already we have seen. Applied force is identical to F of t. Applied force is identical to V of t. Already we have seen. M equal to what? L. B equal to R. That you have to remember. So now we can find the M equal to L, inductor. L1 equal to M1. L1 equal to M1. B1 dx1. What is current through this I1? Current through this is I1. So V equal to what? R. Therefore, R1. This is K1. Therefore, C1. C1 equal to 1 by K1. That's all. This is two variables involved. As far as K2 is concerned, X1, X2. X1, X2. That is Q1 minus. Am I correct? Q1 minus Q2. You will get Q1 minus Q2. Therefore, it involves both the loops, first loop as well as second loop. Therefore, we can write C2 equal to 1 by K2. What is current through this? I1. In this loop, current through this is I1. Here I am going to draw another loop. Here I am going to draw another loop. Here I am going to draw another loop. In that loop, current is I2. What is the current through C2? I1 minus I2. If you write equation for first loop, how you will write? Current through C2 is I1 minus I2. If you write equation for second loop, how you will write? I2 minus I2. I2 minus I1. So consider the second equation. In the second equation, M2, L2 equal to M2. B2, that is C2. B2 is X2 minus X3. We will write later. K2 multiplied by X2 minus X1. Already we have drawn that C2. Instead of K2, already we have drawn C2 equal to 1 by K2. Here it is identical to Q2 minus Q1. Q2 minus Q1. So for this, X2 minus X3, here one resistor is there, that is R2 equal to B2. R2 equal to B2. Current through this is I2 minus I3. And one more, K2 is there, that is one capacitor is there, that is equal to C2 equal to 1 by K2, 1 upon K2. That's all. That's all. How many elements? Inductor, here one capacitor, on 4 elements. Yes. In this loop, 4 elements. Second loop is over. Now we have to draw the third loop. Third loop will be here. Third loop, X2 minus X3. This is in third loop as well as second loop. That's why it comes here. Third loop is here. I will explain one more time. Don't worry. Third loop is here. What is current through this third loop? Current through this third loop is I3. I3. Therefore, here this comes under third loop and second loop. This also comes under third loop and second loop. Now consider the third equation. M3. One inductor is there. M3, that is L3 equal to M3. And this is common to second loop and third loop. Already we have drawn that. R2. This is also common to second loop and third loop. That's all. That's all. This is the analogous electrical system. Analogous electrical system. That's all. Yesterday we have seen how to write differential equation governing the mechanical system. For the given mechanical system we have seen. Now let us see how to obtain electrical analogous system. The first thing is we have to write the mechanical model for this. Now, no need to write free body diagram. The examination you have to draw, but by looking at the diagram, we can directly write. But in the examination, it's better to put a free body diagram for the sake of mass. M1 T square X1 by dt square plus k1 x plus v1 dx1 by dt plus this k2 is connected with m1, therefore k2 x1 minus x2 equal to f of t applied force. This is the first equation. The second equation is m2 d square x2 by dt square. This is for mass. Then for another element connected is this k2. Therefore, k2, here the reference is displacement is x2. Therefore, x2 minus x1 plus k3 x2 minus x3 plus b2 d by dt of x2 minus x3 equal to 0. No applied force. For third mass, m3 d square x3 by dt square plus k3 x3 minus x2 plus b2 d upon dt x3 minus x2 equal to 0. No applied force. These are the three mechanical equations. What is analogous electrical system? M should be replaced by L1. L1 d square q1 by dt square plus k equal to what? 1 by c1 q1 plus r1 dq1 by dt plus k2 again 1 by c2 q1 minus q2 plus equal to v of t applied voltage. Now we know that dq by dt equal to I and q equal to integral of I dt. dq by dt equal to I and q equal to integral of I dt. So if you replace this in terms of I, what you will get? L1 d I1 by dt. Because one derivative reduced. Because dq by dt equal to I, therefore, if you differentiate once again, you will get di by dt equal to d square q by dt square. Therefore, we can write di by dt, L1 di by dt plus 1 by c1, q equal to what? Integral of I dt. Therefore, integral of I1 dt plus dq by dt equal to I. Therefore, R1 I1 plus 1 by c2, q1 minus q2. q1 equal to what? Integral of I1 minus I2 dt equal to v of t. So we got in terms of current. What and all we got? Similarly, for second equation also we can write L2 d square q2 by dt square plus k2 is equal to what? 1 by c2 q2 minus q1 plus 1 by c3 q2 minus q3 plus v2 equal to what? R2 d by dt of q2 minus q3 equal to 0. So if you write this in terms of current, what you will get? L2 d I1 by dt plus 1 by C2 integral of I2 minus I1 dt plus 1 by C3 integral of y q equal to what? Integral of I dt. Therefore, integral of I2 minus I3 dt plus R2 multiplied by I2 minus I3 equal to 0. This is second equation in terms of current. Third equation in terms of charge equal to L3 T square Q3 by dt square plus 1 by C3 Q3 minus Q2 plus 1 by C2 Q3 minus Q2 equal to 0. That's all, no applied force. So if you take this equation, this is the second Kirchhoff's voltage law equation. This, if you write this in current L3 di3 by dt plus 1 by C3 integral of I3 minus I2 dt plus 1 by C2 integral of something wrong here. I2 minus I3, I2 minus I3. Third equation, how many you will get? K3 B2. 1 by C3 B2 equal to B2 equal to what? R2 d by dt of Q3 minus Q equal to 0. That is equal to R2 multiplied by I3 minus I equal to 0. If you consider these three equations, we can draw the electrical analogous of mechanical system. What is the first element? L1. There are three loops are there. Three loops are there. Three loops are there. Three loops are there. The current through the first loop is I1. Current through the first loop is I1. Current through the second loop is I2. Current through the third loop is I3. What is current through this path? In this direction, I1 minus, if you see in this direction, I2 minus I1. If you see in this direction, I1 minus I2. While considering first loop, I1 minus I2. While considering second loop, I2 minus I1. Because we are considering this direction as positive. Okay, three loops are there. If you consider the first equation, L1 di1 by dt, that is only I1 is flowing. Therefore, we can draw this in any one of these three sides. They can draw this in any one of three sides, A, B, C, D. Except BC, you can draw either at AB or AD or DC. So we will write at AB, inductor L1. Then 1 by C1 integral of I1, only current only. That also we can draw at across AB. This is C1. Then R1 I1, that is also I1 only. We can draw either here or here. Only I1 has to flow. We'll draw here R1. L1, C1, R1. Then C2. The current through C2 is I1 minus I2. Therefore, C2 must be here. Two currents are flowing through that. I1 and I2. Then V of t is the applied voltage that is in the first loop only. That is here. V of t. That's all. First equation is over. Consider the second equation. L2 I2. L2 I2 di2 by dt. L2 di2 by dt. Only I2 is flowing. Therefore, we have to draw here L2. Then 1 by C2 I2 minus I1. Already we have drawn that C2. Therefore, no need to draw now. 1 by C3. It is between second loop and third loop. Therefore, it should be here. This capacitor is here. C3. R2. R2 is between I2 and I3. That is also here. R2, C3. How many elements? Inductor 1. This capacitor already drawn. Second, C3 drawn. Third and R2. 4 elements. 1, 2, 3, 4 elements. That's all. So we can complete the second loop. Third loop, L3. Through L3, only I3. Therefore, we have to draw here L3. C3. C3 is between I2 and I3, already drawn. R2 is between I3 and I2, already drawn. That's all. So we can close this. That's all. This is electrical analogous system of mechanical system. This is called voltage analogy. Voltage analogy. Voltage analogy. Force voltage analogy. We can say that force voltage analogy because force is analogous to voltage. Therefore, force voltage analogy. In the same way, we can obtain force current analogy. That is also possible. Force current analogy. For here, what is the source used here? The source is voltage source. Voltage source. If you use a current source, then it is called force current analogy. Force current analogy. What is the difference between voltage source and current source? What is the difference between voltage source and current source? Ideal voltage source, ideal current source. What is the difference? When we can say voltage source is an ideal voltage source? Suppose I am having a 5 volt ideal voltage source means I can take any amount of current from that voltage source. Its voltage remains 5 volt. Voltage remains 5 volt. Then it is called ideal voltage source of 5 volt. Similarly, current source means the current remains constant. Any number of, suppose I am connecting one resistor, the same amount of current flow through that resistor. If I connect 2 resistors in series, then also the same amount of current will flow through this. Then it is called current source. It will give same amount of current irrespective of number of load. It's very difficult to imagine because we practiced to imagine only voltage source. Current source means even voltage will vary, current remains constant. The amount of current given by the source remains constant. A number of parallel paths, if you include, say same amount of current will be divided into many branches. For that, we will use Kirchhoff's current law. That you will see. Force current analogy means the circuit will be with current source. So for this, this is the circuit in which current source is there. One resistor, one inductor, and a capacitor are in parallel. So what is the equation? I1, current through this is I1, current through this is I2, Current through this is I3. What is applied? This current coming from this is I of t. Total current is I of t. I of t equal to I1 plus I2 plus I3. What is current through this path? All are in parallel. That's why voltage is same. Voltage across each element is same. Applied voltage is V. Therefore, I1 equal to V by R. I2 equal to what? L dV by dt plus what is 1 by L, 1 by L integral of V dt. Voltage across the inductor is 1 by L V dt plus C dV by dt. Voltage across the current through the capacitor is C dV by dt. The current through the inductor is 1 by L, 1 upon L integral of V dt. So the equation is 1 upon L integral of V dt, V by R, C dV by dt. This is one is I1, this is I1, I2 and I3. Total current is I. Always it remains same for a current source. But we know that V equal to rate of change of flux d phi by dt, or phi equal to integral of V dt. If we bring this dt this side and integrate on both sides, we will get phi equal to integral of V dt. This you should remember. Therefore, we can write V equal to d phi by dt. Therefore, dV by dt equal to d square phi by dt square. C d square phi by dt square. V equal to what? D phi by dt. So we can write like this. Integral of V dt equal to phi. Therefore, phi upon L. So we can write in terms of phi also. Rate of change of flux equal to voltage. This is rate of change of flux equal to applied voltage across the element. So this is identical to mechanical equation. You go to that again. This sum, it's again. What is the first equation? M1 d square x1 by dt square plus K1 dx1 by dt plus B1, K1 x1 plus B1 dx1 by dt plus this K2. For this K2, we can write K2 multiplied by x1 minus x2 equal to applied force F of t. So now we can write in terms of force current analogy. Force current analogy. So force current analogy is M is identical to C. X is identical to flux. B is identical to 1 by R. Dx by dt equal to V. Already we have seen. K equal to 1 by L. K equal to 1 by L. B is 1 by R. Earlier B equal to R. Now B equal to 1 by R. Anyhow, there is no change in B. Earlier R. Now 1 by R. But earlier in the force voltage analogy, M is identical to L. Similarly, K is identical to C, 1 by C. Here 1 by L. That is the only difference. Instead of R, earlier B is identical to R. Now 1 by R. That is the difference. So wherever you find M, replace by C. Replace by C. Wherever you find B, replace by 1 by R. wherever you find K replaced by 1 by L, you will get electrical force current analogy. So what we have to do, wherever you find M replaced by C1 d square phi 1 by dt square plus K1. What we have to do for K? For K, what we have to do? 1 by L. So we have to put 1 by L1. 1 by L1 phi 1 plus B equal to 1 by R1 d phi 1 by dt plus K2 should be replaced by 1 by L2 phi 1 minus phi 2 equal to I of t. Now we have to write in terms of voltage. D phi by dt equal to what? Voltage. Therefore, C1 d V1 by dt plus 1 by L1 phi equal to what? Integral of, we have already written this. Phi equal to integral of V dt. Therefore, integral of V1 dt plus d phi by dt equal to V. Therefore, V1 by R1 plus 1 by L2. 1 by L2. Therefore, 1 by L2 integral of V1 minus V2 equal to I of t. We got one equation. The same way we can write for mass 2. M2 d square x2 by dt square plus K2 x2 minus x1 plus K3 x2 minus x3 plus B2 dx2 upon dt x2 minus x3 equal to 0. If you replace this by current analogy, C2 d square phi 2 by dt square plus K2. K2 means 1 by L2 phi 2 minus phi 1 plus K3 1 by L3 phi 2 minus phi 3 plus B2 equal to 1 by R2 d by dt of phi 2 minus phi 3 equal to 0. So now we can write in terms of voltage C2 dV2 by dt plus 1 by L2 integral of V2 minus V1 dt plus 1 by L3 integral of V2 minus V3 dt plus d phi by dt is voltage V2 minus V3 divided by R2 equal to 0. This is second equation. We have to write the third equation. What is third equation? Third equation is M3 d square x2 x3 by dt square plus K3 x3 minus x2 plus B2 d by dt of x3 minus x2. No applied force, therefore equal to 0. This is third equation. If you write in terms of current, M3 is C3 d square phi 3 by dt square plus what is K3? K3 should be replaced by 1 by L3. 1 by L3 phi 3 minus phi 2 plus 1 by R2 d by dt of phi 3 minus phi 2 equal to 0. Now, if you write in terms of voltage, d phi by dt equal to V voltage. If you write to use that, you will get C3 d phi 3 by dt. Sorry, dv3 by dt plus 1 by L3. Phi equal to integral of V3 minus V2 dt plus 1 by R2 multiplied by V3 minus V2 equal to 0. This is third equation. Three equations are there. Three equations are there. This is one equation. This is second equation. This is third equation. Now we have to draw the circuit, that's all. KCL circuit. We are doing in the reverse direction. In circuit theory, electric circuit analysis, for given circuit you wrote KCL. Here, for the given equation, you have to draw the circuit, that's all. Reverse process. So first equation consists of how many elements? 1, 2, 3, 4, 5 elements, including I of t. How many voltages are there? V1, V2, V3. Therefore, 3 nodes are there. If you include one more reference node, 4 nodes are there. 3 equation means 4 nodes. One node will be taken as a reference node. So what we can do is, we have to take one reference node. We have to take one reference node. This is the reference node. Reference node. Another 3 nodes. One is V1 node. Another node is V2 node. Third node is V3 node. 3 nodes are taken. V1, V2, V3. One node taken as a reference. If 4 nodes are there, we will write 3 equations. One node will be taken as reference. Then we will go to the first equation. First equation says C1 dV1 by dt. It is the voltage across this capacitor is only V1 only. Therefore, what we have to do is across V1 and reference, we have to draw the capacitor C1. Then again go to that equation. Second, L1 by L1 integral of V1. Again, only V1. Therefore, we come here and draw an inductor and connect to the same reference L1. Again, go to that equation. V1 by R1. V1 upon R1. One resistor, only applied voltage is V1 only. V1 only. Therefore, again, take here one resistor R1. Then go to this circuit. 1 by L2, voltage across V1 and V2. This inductor is across V1 and V2. Therefore, what we have to do is, we have to draw this inductor between V1 and V2. This is V2. This is V2. L2 is between V1 and V2. Then again come here. The right hand side is the applied current source is I of t. That also in the first node. In the first node. Therefore, we can draw that also. Current source in the first node, I of t. That's all about first equation. Now go to the second equation. Second equation, C2 dV2 by dt. Only across C2, only V2 is applied. Therefore, the C2 will be like this. C2. Between V2 and reference. Come again. L2 is between V2 and V1, already drawn. L2 is between V2 and V1. See that? L2 is between V1 and V2. L2 is between V1 and V2 already drawn. L3 is between V2 and V3. L2 is between V2 and V3. L2 is between V2 and, L3 is between V2 and V3. And R2 is between V2 and V3. R2 is also between V2 and V3. That is also between V2 and V3. R2. Yes, R2. R2 is between V2 and V3. R2 is between V2 and V3. No sources in node 2 and node 3. That's all for about second. Third node. C3 is between V3 and reference. Here, C3 is between V3 and reference. Therefore, we have to draw one more capacitor between V3 and reference. That is C3. Then come to that equation. L3 already drawn. L3 already drawn. R2 already drawn. That's all. This is a circuit, but it looks ugly. Huh? That's why we have to draw again. We'll draw here. We'll draw here. Current source I of t. R1, C1, L1, then this is V1. This is also V1. This is also V1. No element is connected. That's why all are in V1. Between V1 and V2, this is V2. L2 is connected. L2 is connected. Between V2 and C2, between V2 and C2, between V2 and reference, C2 is connected. This is reference. Between V2 and V3, L3 is connected. This is V3. Between V3 and V2 and V3, R2 is connected. Between V3 and reference, C3 is connected. That's all. Now it looks good. Same circuit, but we redrawn like this. This is to understand. So everything is between reference and some node. That's why I drawn like this. But both are same. This is force current analogy of given mechanical system. Force current analogy of mechanical system. Current source is theoretical source. Current source is theoretical source. Nowadays, current sources are available. Current sources are available, but you cannot buy like battery like current source. A device will be available that will give constant current. That will give constant current. Such current sources are available. So you can do this experiment also. So if you want to simulate a mechanical system in the electrical way, you have to find this analogy. Obtain the mathematical model. Write, do it yourself. Obtain the mathematical model of the mechanical system shown in figure. How many equations you will get? 3 equations, because 3 masses are there, M1, M2, M3. That's why you will get 3 masses. Draw free body diagram, then write the equation. What are the forces acting on it? Displacement in M1 is x1, displacement in M2 is x2, displacement in M3 is x3. The first equation is m1 d square x1 by dt square plus k1 x1 minus x2. Why? Because it is connected between first mass and second mass. That's why x1 minus x2 plus b1 d upon dt of only x1, because another reference is one end is connected to mass 1, another end is connected to reference, equal to 0. No applied force in the first mass. What is second equation? m2 d square x2 upon dt square plus k1 x2 minus x1 plus k3. One end is fixed to m2, another end is reference. That's why k3, another end is fixed. Therefore, k3 x2 only plus b2 d by dt of x2 minus x3. Applied force is there, f of t, therefore equal to f of t. This is second equation. Third mass, m3 d square x3 by dt square plus, we can write b2 d upon dt of x3 minus x2 plus k2 multiply, one end is fixed, therefore k2 x3 equal to 0. No applied force. That's all. 3 equations we got. Now let us find force. Let us find force voltage analogy. Force voltage analogy. For that, what we have to write? L1 d square q1 by dt square plus k1 equal to what? For force 1 by c1. 1 by c1 q1 minus q2 plus r1 dq1 by dt equal to 0. This can be written as L1 d I1 upon dt plus 1 by c1 integral of I1 minus I2 dt plus dq by dt, dq q1, yes, q1 is I1, R1 I1 equal to 0. Similarly, if you consider the second equation, what you will get? L2 d I2 by dt, directly you will write di2 by dt plus k1 equal to what? 1 by c1 I2 minus I1 dt integral plus k3 1 by c3 integral of I2 dt plus b2 r2 multiplied by I2 minus I3 equal to f of t. Sorry, v of t. V of t. This is second equation. This is first equation. This is second equation. Third equation, L3 di3 upon dt plus time up 1 minute. We'll write the third equation and finish. L3 di3 by dt plus what is 1 by P2 equal to 1 by C2. P2 equal to 1 by C2, sorry, R2. R2 I3 minus I2 plus K2 equal to what? 1 by C2 integral of I3 dt equal to 0. That's all. So now we have to draw the circuit. We have to draw the circuit. There are three equations. Here, you have to notice that I2 minus I3. So there is element between second loop and third loop. Second loop and third loop. Second loop and third loop. If you consider the first equation, first loop and second loop, sometimes 1 and 3 will come. No such problem here. That's why only 3 loops. 3 loops are there. The first loop L1 is there. Current through this is I1. Current through this is I2. Current through this is I3. The first loop L1 is there. L1. C1 is between first loop and second loop. C1. R1 is in the first loop only. So we can draw here R1. That's all. In the second equation, if you consider the second equation, where it is written, directly we wrote L2. L2 is in I2 only. L2 is in I2 only. L2. I1 minus I2, C1 already drawn. C3 is in second loop only. C3 is in second loop only. So we can draw here. C3 is in second loop. R2 is between second loop and third loop. R2 is between second loop and third loop. Applied voltage is V of t. That is also in this loop. Therefore, we have to draw here or here. In this loop only, not a common. Therefore, we will draw here. That is V of t. V of t. That's all about this V of t. It should be positive. The direction, this should be positive. While writing V of t, this should be positive because in the current direction, it should be positive. Okay. Then third loop, L3 is there. The third loop, L3 is there. R2 is between, already we have drawn, 1 by C3. C3 is there. This is in this loop only. So we can draw here, C3. That's all. This is force voltage analysis. See, C2 is which equation? L3, R2, C3. Only 3 elements only. Mass. This is resistance. This is that's all. This is capacity. This is inductance. This is capacitance. This is resistance. Only 3 elements. Obtain the mathematical model of system shown in figure. Here, 3 masses are there. M1, M2, and M3. And finally, obtain the electrical force voltage analogy. Force voltage analogy of given mechanical system. And hence find Find force voltage analogy of given system. Here, what are the forces acting on M1 because of K1, because of K2, and FV1, FV1, FB1, or simply B1. These are all dashpot coefficient, frictional coefficient. Sometimes they will put like this. That's why I took this out. Because of frictional force, this dashpot effect will be there. That is mentioned as FV1. Here FV2. Between two masses also that is mentioned. They mentioned FV3 and FV4. FV4. The displacement of mass 3 is x3. This is x3. Displacement of mass m1 is x1. So what are the applied force? Applied force is on m2 only, f of t. Now, if you draw the free body diagram for m1, displacement is to its right. F, no force, no applied force. Displacement is x1 to the right. Therefore, reaction forces are acting from right to left because of F, M1, because of K1, because of K2, and because of FV1, of course, because of FV3. These are the 5 reaction forces acting on M1. Fm1 is M1 d square x1 by dt square plus Fk1, one end is fixed. Therefore, K1 x1 plus K2, both ends are free. Both ends are free. Displacement at this end is x1, displacement at this end is x2. We are writing in terms of M1, therefore, K2 multiplied by x1 minus x2. Here, the friction is between floor and the mass m1. Therefore, one end is fixed in this case. Therefore, plus Fv1 d upon dt of x1. That's all. But for Fv3, between m1 and m3, the displacement in m1 is x1, displacement in m3 is x3. Therefore, d upon dt of x1 minus x3. How many forces? 1, 2, 3, 4, 5. That's all. Equal to 0. Therefore, no applied force. No applied force. Similarly, if you write for M2, M2 d square x2 by dt square plus because of K2 x2 minus x1 because of Fv2 d upon dt of x2 plus because of Fv4 d upon dt of x2 minus x3. How many forces? Because of M1, 2, 3, 4. That's all. 4 reaction forces. 1, 2, 3, 4 applied force is F of t. That's all. Then for M3 d square x3 by dt square plus no spring, only dash part. Dash parts are FV3 and FV4. That's all. Therefore, no applied force. So FV3 d upon dt of x3 minus x1 plus FV4 x3 minus x2 equal to 0. No applied force. Only three reaction forces. Only three reaction forces. Now we got the mathematical model of given mechanical system in time domain. That's all. These three equations together represent the given mechanical system. I took this sum because of two reasons. One is to explain FE1, FE2, FV3 and FE4. Frictional coefficients can be taken as dashpot coefficients. That is one thing. Another thing is here the electrical system will get some difficulties in uptake. That's why. That we'll see now. How to convert this into force voltage analogy. For that, what we have to do is we have to take L1 force voltage analogy. L1 d square q1 upon dt square plus k. K equal to what? 1 by C1 Q1 plus 1 by C2, 1 upon C2 Q1 minus Q2 plus FV1. FV1 is B. B should be taken as R. RV1. RV1 or R1 simply. R1 dQ1 upon dQ1 upon dt plus R3 d upon dt of Q1 minus Q3 equal to 0. For second equation, L2 d square Q2 upon dt square plus K2 1 by C2. 1 by C2 already we returned in the previous equation. We have to reverse that. Q2 minus Q1 plus FV2. FV2 is R2. R2 dQ2 by dt plus FV4. FV4 is what? R4 d upon dt of Q2 minus Q3 equal to V of t, applied voltage. Here we can write for third equation L3 d square Q3 upon dt square plus FV3 is R3 d upon dt of Q3 minus Q1 plus R4. R4 already we wrote. We have to reverse that. Q2 minus, sorry, Q3 minus Q2 d upon dt of Q3 minus Q2 equal to 0. Now we can write all these equations in terms of current. We wrote in terms of charge. We know that I equal to dq by dt. Replace in terms of current. What you will get? The first equation is L1 d square, sorry, di1 by dt plus 1 by c1 q equal to what? I equal to dq by dt. Therefore, q equal to integral of I dt. Therefore, 1 by c1 integral of I1 dt plus 1 upon c2 q1 minus q2. Therefore, 1 upon c2 I1 minus I2 dt. I1 minus I2 dt. R1 dq by d is I1. Therefore, plus R1 I1 plus R3 I1 minus I3. R3 I1 minus I3 equal to 0. 1, 2, 3, 4, 5. This is first electrical equation. For second, L2 di2 upon dt plus 1 upon c2 I2 minus I1 dt plus R2 I2 plus R4 I2 minus I3 R4 I2 minus I3 equal to V of t. This is second equation. Third equation, L3 di3 by dt plus R3 I3 minus I1 plus R4 I3 minus I2 equal to 0. Only 3 forces acting on it. This is third equation. Now we have to draw the equation. You see that in the first equation, I1 minus I2. Therefore, first loop and second loop are adjacent. First loop and second loop are adjacent. In the same first equation, one more I1 minus I3. Therefore, first loop and third loop also is adjacent. First loop and third loop also adjacent. Here, I1 minus I2, first loop and second loop. I2 minus I3. Second loop and third loop also adjacent. Second loop and third loop also adjacent. First and third, second and third. Here, I3 minus I1. First loop, third loop and first loop are adjacent. I3 minus I2. Second loop and first loop are adjacent. But anyhow, if you see that first loop and the second loop are adjacent, no problem. That is already we have seen such type. This is I1. This is I2. No problem. I1 minus I2 automatically you will get. We need I1 minus I3. Therefore, it should be adjacent to first loop as well as second loop. Here you will get I1 minus I3. Here what you will get? I3 minus I2. I3 minus I2. I3 minus I2. I3 minus, here you will get I3 minus I1. Or I1 minus I3. Here I2 minus I3 you will get. So this is the problem. If you take the loop like this, you can finish. This is the crucial point. That's why I took this up. So L1 is in the first loop only. Therefore, we can draw L1 here in the first loop only. R3 is between I1 and I3. R3 is here. C1 is in I1 only. C1 is in I1 only. C2 is between I1 and I2. C2 is between I1 and I2. R1 is in I1 only. R1 is in I1 only. We can put here. R1 is in I1 only. 1, 2, 3, 4, 5. That's all. If you take second loop, L2 is in I2 only. So we can draw L2 here. C2 is between, already we have drawn, C2 is between I1 and I2. R2 is in I2 only. R4 is between I2 and I3. Therefore, R4 must be here. How many? 1, 2, 3, 4 elements. Yes, 4 elements are there. We can finish. But one thing is pending, that is V of t. That is in this loop only. So V of t is applied here. V of t. So the capacitor, I have to remove this. Some line is there. Be careful. Okay. This is capacitor, remarked. So you can mind those things. L3 is in third loop only. L3 is in third loop only. We can draw here L3. R3 is between third loop and first loop, already drawn. R4 is between second loop and third loop. That's all. That's all. This is electrical analogous of given mechanical system. Force voltage analogy. Do it yourself. Force current analogy. Assignment number question 1 is find the current analogy. The solenoid shown in figure. The solenoid shown in figure produces a magnetic force proportional to current. Proportional to current. Proportional to the current I in the coil. F is the coil. F is the coil. This is the coil, solenoid F. In that, a force is produced. You know that if you wind a coil and supply current, it becomes electromagnet. If you put any iron outside that coil, parallel to that, like this. If you put any iron here, it will move inside automatically because of a force developed. Force developed by this coil, it will move. This iron will move inside. Permeability, less 800 times less than the air. That's why this iron will move inside. A force is developed. That is sufficient. The force developed in the coil is equal to Ki1. This is, instead of applying a force at this end, we can say that a force F of t is applied at this end. We can say instead a coil is given. That's all. So a current is applied I of t. Sorry, a voltage is applied E of t. Because of that, there is a current in the coil I of t. So a force is developed in the coil. That force is F of t. The coil has an inductance of L, resistance R. This is property of the coil. The coil develops a force F. The coil takes a voltage of E of t. The current through the coil is I of t. The inductance of the coil is L. The resistance of the coil is R. the force developed is F. The force is equal to K1 times I. K1 times I, where I is the current through the coil. That's all. Instead of giving simply force, it is given like this to make you confused. In addition that, it has some mechanical property also. This coil has a weight of M1. The coil has a mass M1. The coil has another property because this coil is, the other end of the coil is attached to the fixed surface through B1. Dashpot constant B1. These are the two properties. This beam is, the length of the beam is L1 plus L2. At this point, the beam is hinged. You know what is meant by hinged? Hinged means the door is hinged. One end is hinged. That's why you can move this door. Like that, this beam is hinged at this point. That's why it can move up and down, depends upon the force. This end also moves up and down. About this point O, about this point O, the other end is fixed to mass M2. The other end is fixed to mass M2. The mass has the property of spring K2 and dashpot constant B2. Now, what is the direction of displacement that we have to see? If we see that because of the force developed by this coil, the displacement at this end A is x1. At this end B is definitely, if A comes down means B will go up. B will go up. Therefore, the force developed by M2, K2, B2 are downward. Why? Because X2 upward. X2 is upward. Therefore, the force developed by M2, K2, B2 are downwards. Here, the applied force is F. That is downward. That's why displacement is downward. Therefore, reaction forces developed by M1 and B1 are upward. M1 is upward because of B1 also upward. M2 is downward here, this end. But anyhow, the reaction forces are trying to rotate the beam in the clockwise direction. Am I correct or not? The reaction force M1, B1, FM2, FK2, FB2. All the 5 reaction forces try to rotate the beam in the clockwise direction. But the force F try to rotate the beam in the anti-clockwise direction. Am I correct or not? Therefore, if we take moment, clockwise moment and anti-clockwise moment are equal. Therefore, I can say that F1, L1, this is what? Clockwise moment or anti-clockwise moment? Anti-clockwise moment. Anti-clockwise moment is F1, L1. Force developed at this end. Therefore, F1, L1 is the anti-clockwise moment. That must be equal to all reactional forces. All reactional forces, they try to rotate in the clockwise direction multiplied by distance where it is applied. But some forces are applied at a distance x1, L1. Some forces, some reaction forces applied at a created at a distance L2. Some reaction forces created at a distance L1. Some reaction forces created at a distance L2. Therefore, we can write F reaction forces 1 multiplied by L1 plus F reaction force 2 multiplied by L2. Two forces. Two forces, reaction forces. If you convert this into moment, it means we have to force multiplied by distance. Anti-clockwise moment, Y F1, L1. The force is at this end at a distance of L1. the moment equal to F1 L1. Anti-clockwise. Clockwise moment developed this end as well as that end. This end because of M1 and B1, that should be multiplied by L1. This end M2, B2, K2, that should be multiplied by L2. That's all. That's all about the mathematical model. So what is the mathematical model? The first equation is F equal to K1. Already it is given, but anyhow, it is also part of mathematical model. Second one is F1 L1. F1 L1 equal to F1 L1 equal to the clockwise moment developed this side are M1 d square x1 by dt square multiplied by L1 plus another force V1 dx1 by dt multiplied by L1. Therefore, we can write multiplied by L1 plus in this end, what are the reaction forces developed? Because of M2, therefore, M2 d square x2 by dt square multiplied by L2 plus V2 dx2 by dt L2 multiplied by L2 plus K2 x2 all should be multiplied by L2. That's all. So what you got? So f of t L1 equal to M2 d square x2 by dt square plus K2 x2 plus B2 dx2 by dt multiplied by L2 plus V1 dx1 by dt plus M1 d square x1 by dt square multiplied by L1. I wrote the first second. That's all. If you equate these two moments, you got this equation. You got this equation. Now divide on both sides by L1. So this L1 getting cancelled. Divide on both sides by L1. L1 getting cancelled. But we know that the displacement is very small. This is the distance L1. This is L2. The displacement is x1. Here the displacement is x2. If you consider these two are similar triangles, because displacement is very small, not arc, very small displacement x1 and x2. That's why we can take it is similar triangles. Sides are L1. Base is x1, x2. Therefore, we can say that L1 by x1, L1 upon x1 equal to L2 upon x2. But I want to obtain the mathematical model. Write the differential equation. That's all. Mathematical model is over. We wrote the differential equation. We wrote the differential equation. Time domain mathematical model is over. But the second part of the question is, hence determine the transfer function x2 of s upon e of s. But x1 should not be there. To find this transfer function, x1 is another variable. X1 must not be there. That's why we found this relation. Wherever you find x1, that can be replaced by L1 upon x1 equal to L2 upon x2. Therefore, x1 equal to L1 upon L2 multiplied by x2. X1 equal, from this we can write x1 equal to L1 upon L2 multiplied by x2. Now we can write this equation. Now we can write this equation, can be written as f of t equal to L2 upon L1 M2 d square x2 upon dt square plus B2 dx2 upon dt plus k2 x2 plus we can replace x1 by L1 by L2. Therefore, here also we will get L1 upon L2. Here, this is V1 dx1. We want to write dx2 in terms of x2. Therefore, L1, this constant came out. There is no differentiation for constant. x2, if we differentiate x2, dx2 upon dt, b1 multiplied by b1 plus m1 d square x2 upon dt square. So the entire equation in terms of x2. Now the entire equation is in terms of x2. Now we can take Laplace transform assuming zero initial conditions. Now we can find. Now we can find this equation can be written as take Laplace transform on both sides f of s assuming zero initial conditions. F of s equal to L2 upon L1 M2 s square x2 of s plus V2 s x2 of s plus k2 x of s x2 of s plus L1 upon L2. If we take Laplace transform of this, what you will get? B1 s x2 of s plus m1 s square x2 of s. That's all. So now you can bring x2 of s one side. What is the transfer function required? Laplace transform of output upon input. Input is E of s. But here it is in terms of f of s. So now take this. What is the relation for f of s? We have to take E of s. We have to take, that is E of s equal to, we write Laplace transform. Let it be A. E of s equal to L s I of s plus R I of s. That is equal to Ls plus R multiplied by I of s. Let it be B. Here, if you take Laplace transform, you will get f of s equal to k1 I of s. From here, you can substitute I of s. From B, you can substitute I of s from B. I of s from B equal to what? E of s upon L s plus R. Therefore, f of s equal to k1. I of s equal to what? E of s upon L s plus R. This is D, equation D. Substitute D in A. F of s can be replaced by k1. Now I am simply replacing here. F of s can be replaced by k1 E of s upon Ls plus R. So find x of s upon E of s, because E of s is the input. You see the diagram. What is input here? Input to the system is E of S. The output is X of X2. X2 is the output. That's why Laplace transform of output upon Laplace transform of input that we have to find. The transfer function model we have to find. So here, if you come here, X2 of S is available, the right hand side. E of S is available, the left hand side. What we have to find? Output by input. Therefore, X2 of S upon E of S equal to, this will come down. This also will come down. Therefore, what you will get is E of S K1 upon Ls plus R multiplied by L2 upon L1 M2 S square plus B2 S plus K2 plus L1 upon L2 Bs plus M1 S square whole bracket. That's all. This is the transfer function of given mechanical system, assuming that X2 is output, E is input. That's all. X2 is output, E is input. Applied voltage is the input. This is the transfer function model of given mechanical system. Transfer function model of given mechanical system. Mathematical. In the next class, we'll see mathematical modeling of armature controlled DC motor and block diagram. That we'll see in the next class. Mathematical model of armature controlled DC motor. Armature controlled DC motor. This is the armature. But the armature resistance and inductance are mentioned here. A torque will be developed in the armature. That is called Tm. The mechanical torque developed in the armature. That's why it is rotating. That's why it is rotating. What is back EMF? Back EMF. Back EMF is EMF generated in the armature of motor. Armature of motor. What is generator? If you rotate the armature in the magnetic field, EMF is induced. That is generator, DC generator. Because it cuts the flux, that's why EMF is generated. Here, the opposite. Fleming's left-hand rule. Magnetic flux is placed, you are rotating instead of placing, instead of rotating, we are placing in the magnetic field. Fleming's left-hand rule, that's why it starts rotating, but the coil is in the magnetic field. Right-hand rule also applied, no? Why it is rotating? Because the coil is placed in the magnetic field. That's why Fleming's left-hand rule, it starts rotating. But Lenz's law, an EMF is induced, the cause which produced opposes the cause which produces. Lenz's law. As per Lenz's law, there is a back EMF. That is generator principle. You can think like that. Even though it is a motor, the coil is rotating in the magnetic field. That's why there will be an EMF will be induced. That is back EMF. Therefore, if you apply a voltage EA across this armature, you are applying a voltage EA. There is a drop in the coil, that is LA DIA by dt. And drop in the resistance of the armature coil, RAIA. And there is a back EMF which opposes the applied voltage. So three components are there. Normally for a coil, only two components. Since it is rotating in the magnetic field, there is a back EMF EB. Therefore, EA equal to LA DIA by dt plus RAIA plus EB. This is because of the rotation. EB is because of the rotation. So the applied voltage EA equal to LA DIA by dt. That is potential drop in the coil, potential drop in the resistance plus back EMF. What is the torque developed in the armature? Torque, the mechanical torque developed in the armature equal to proportional to armature current. The torque developed in the armature is proportional to armature current. To make it equal, the KT constant. So Tm equal to KTIA. That is the mechanical torque developed in the armature. But this armature is connected to a load. Connected to a load. That load has an inertia of J. Load has an inertia of J and a dashpot V. Therefore, this mechanical torque equal to J d square theta by dt square plus d theta by dt. This is first equation. This is second equation. This is third equation. These are the three equations. Why it is called armature controlled DC motor? How we can control speed of a DC motor? How we can control the speed of DC motor? What are the methods available? N is proportional to V minus EB upon phi. So any change in V applied voltage, that is VA or EA, we can say. If you change this EA, there will be a change in speed directly proportional. That's why if you want to change the speed, if you want to control the speed of this motor, simply you can adjust this applied voltage. That is one way. Another way is if you decrease the flux produced by this coil. This is the flux given by this. For this armature, you need a flux. The flux will be generated by this field coil. This field coil will produce flux. If you adjust this flux to reduce the flux, that is reducing the voltage, you can reduce the flux. By that also you can increase the speed. If you increase the flux, there will be a decrease in speed. So in the opposite way, that is also possible. But here, if you adjust this applied voltage across the armature, then it is called armature controlled DC, because we are controlling the speed by controlling the voltage across armature. If you adjust the speed by adjusting the field, then it is called field controlled DC. We are not adjusting any field current. That's why there is no change in field. So this is constant. That's why we are not including this in the mathematical model because it remains constant. We are assuming that field remains constant. Then why we have to obtain the mathematical, why we have to include? No need, because the equations are for changes. The equations are for changes that you will see later in the next semester. In process control, you study all those things. Now it's very difficult to explain. There is no change in the field. That's why there is no equation for that. But if you control by field means that equation also will be improved. So only this equation is written already. That's all about electrical equation. For mechanical electrical relation, there is one equation. The mechanical torque developed equal to kT times Ia, that is second equation. Then a mechanical equation, because the armature connected with a load whose inertia is J, dashpot constant is B. Therefore, Tm equal to, the displacement in the armature is theta. Therefore, Tm equal to J d square theta by dt square plus B d theta by dt. That we know. Already we studied for the rotational system, mathematical model of rotational system. So we got three equations. But we know that the back EMF, how back EMF is generated, a coil is rotating in the magnetic field. That's why there is an EMF induced. That EMF opposes the applied voltage. Lenz's law. So it is proportional to speed of that armature. Proportional to back EMF is proportional to speed d theta by dt. If you make it equal, you are multiplying by kb. Therefore, EB equal to kb d theta by dt. That is fourth equation. Instead of putting d theta by dt, you can put omega also, kb omega, or speed, number of rotations n. Here, EB equal to kb d theta by dt. That's all. These are the four equations represent the armature controlled DC motor. Four equations represent the given armature controlled DC motor. Now, we will obtain the transfer function. For that, we have to take Laplace transform of this E A of S equal to LAS, assuming zero initial conditions. LAS IA of S plus RA IA of S plus EB of S. That is also a variable. This is equation A in frequency domain. Tm of S equal to Tm of S KT IA of S. This is second equation, B. Next equation is Tm of S equal to J S square theta of S. Assuming zero initial conditions. B S theta of S. This is another equation in frequency domain. To write for this EB of S equal to KB theta S theta of S. This is the equation. If you combine all these things together, you will get the transfer function. What is the input to the armature controlled DC motor? Transfer function model of armature controlled DC motor. So what we can do is, here we can take this IA of S outside, and IA of S can be substituted from here. Then you can substitute Tm of S in that. Everything will be in terms of theta. You will get. Then EB of S, in place of EB, if you substitute this, you will get back EMF also comes in terms of theta. So we can write now E A of S equal to LAS plus RA multiplied by IA of S plus KBS theta of S. Why? Because D says EB equal to KBS theta of S. That's why we wrote KBS theta of S here. Now, IAS can be replaced by TM by KT. So LAS plus RA. IAS equal to what? From the equation B, we can write TM by KT. TM of S upon KT plus KBS theta of S. Now, TM equal to what? TM of S equal to JS square. Yes, JS square theta of S plus BS theta of S. So instead of TM of S, we can substitute LAS plus RA. Instead of TM, we can substitute this. We can substitute this equation. TM equal to TM of S equal to JS square plus BS multiplied by theta F S can be substituted. Therefore, instead of TM, JS square plus BS theta of S upon KT plus EB, for EB equal to BS theta of S. So everything in terms of theta S now. Now we can find theta of S upon EA of S. So what we can do is theta, therefore theta of S upon KBS theta of S. Therefore, theta of S upon EA of S equal to, you bring everything here, what you will get? If you take KT as LCM, you will get KB KT upon KT. Am I correct? I am taking LCM KT. Therefore, here you will get KT in the numerator. KT in the numerator. In the denominator, you will get LAS plus RA multiplied by JS square plus BS plus KB KT S. That's all. So this is the transfer function model of given system. Transfer function model of given system. Transfer function model of given system. Once again, we'll see what is the armature controlled DC motor. DC motor can be controlled in two ways because we have the relation N equal to VEA minus EB. EA minus EB upon 5. Either you can control the speed by adjusting EA or by adjusting flux. The armature control DC motor, we are not adjusting the flux. Flux remains constant. That's why there is no equation for this field part. We are writing equation for this part only. By adjusting EA, we are adjusting speed. That's why it is called armature control DC motor. The first equation is, it has armature resistance, inductance, and back EMF. So therefore, the first equation is EA equal to applied voltage equal to LA DIA by dt, because current through the inductor is IA, armature current, IA. current through the inductor is, current through the armature is IA. Therefore, LA DIA by dt plus RA IA plus back EMF EB. If you take Laplace transform, you will get EA of S equal to LA S by assuming zero initial condition. LA S IA S plus RA IA S plus back EMF. If you write KB EB of S, sorry, EB of S. But EB of S equal to what? EB of S equal EB equal to, we know that EB equal to KB d theta by dt. If we take Laplace transform, EB of S equal to KB S d theta. That is substituted here, KB S d theta for EA of S. We know that TM equal to KTIA because mechanical torque developed in the armature is proportional to armature current. Therefore, Tm equal to KTIA. If we take Laplace transform, Tm of S equal to KTIAS. That is second equation. We know that this armature is connected to a load whose inertia is J, dashpot constant is B. That's why the mechanical torque equal to J d square theta by dt square plus B d theta by dt. Because theta is the displacement. Theta is the displacement. If we take Laplace transform, Jm of S equal to Js square theta of S plus Bs theta. If you substitute in EA of S equal to LAS plus RA into IA of S plus back EMF equal to KB S theta of S. From here, from D equation we substituted. Now, IA equal to what? From the Tm equation, we can substitute IA equal to Tm by KT. Tm equal to Tm equal to Js square theta of S plus Bs theta of S. Therefore, Tm can be replaced by Js square Bs plus theta of S by KT. If you take LCM using KT, the numerator also becomes KB KT S theta of S. So if you find theta of S upon EA of S, why we have to find? Because theta is the output. Sorry, EA of S. Applied voltage is EA of S. If you find that from this relation, we can write that KT is the denominator, that becomes in the numerator, KT upon LAS plus RA multiplied by JS square plus BS plus KB KTS. That's all. This is the transfer function model. Transfer function model of armature controlled DC motor. How this armature controlled DC motor is represented here by electrical circuit. By electrical circuit. Electrical representation, electromechanical representation. But I want to represent this in a block diagram model. Most of the equations will be represented in block diagram by transfer function model. So if I find the transfer function, this can be represented as a block diagram like this. I found the transfer function of the armature control DC motor, that is theta of S upon EA of S. That is the transfer function. Input is EA of S, output is theta of S. This representation is called block diagram. Block diagram, not black, block diagram. Block diagram. We can represent like this. We have to put a box. The transfer function can be called as GA of S equal to theta of S upon EA of S. We can call the transfer function as GA. A is for armature control DC motor. GA of S. So in the block diagram, we can write GA of S simply. The input is EA of S and the output is theta of S. We can put like this. This representation is called block diagram representation. But there is no inner details. The final transfer function is represented like this. But we can find the block diagram for each and every equation. Every equation has input and output. For every equation, we can find one block. So we can, how we get this transfer function? By combining all these equations. So we need a mathematical manipulation is required. But if you represent each equation by a block diagram, we will get block diagram representation. Block diagram representation. That also can be used to find the transfer function. That also can be used to find the transfer function that we will see now. Now, what is the first equation? The first equation is EA equal to EA of S equal to LA S plus RA IA of S. Am I correct? Plus EB of S. This is separate. So instead of combining, because it is in different variable, this is different variable. So what I can do is, I can put EA of S minus EB of S as one variable equal to LA S plus RA multiplied by IAS. Let us assume that IAF is the output. EA minus EB, if you give EA minus EB as input, it will give IA current. That way I can represent the model, you know. So the output is IA of S. I am assuming that output is IA of S. Input is EA minus EB. I am leaving S EB equal to 1 upon LAS plus RA. 1 upon LAS plus RA. You got one transfer function. In this case, the input is EA minus EB, output is IA, armature current. I got one model, block diagram representation. For this, I can put like this, one block I can put. It is called IA upon EA minus EB. The input is EA minus EB. Output is IA. I can put. So this equation can be represented like this. Next equation, what is the next equation? TM of S equal to JS square plus BS multiplied by theta of S. Am I correct? TM equal to JS square plus BS theta of S. One more equation. TM equal to KT IA of S. So what is the transfer function? If you take this, this is the equation B, this is C. So first let us see B. The input is IA, output is TM. TM upon IA of S. TM of S upon IA of S equal to KT. This is another equation, another block diagram. What is the input for this? KT is the transfer function. Input is IA, output is TM. This can also be represented in block diagram. Output is theta of S. Input is TM of S. That is equal to 1 upon J S square plus BS. This is another block. This block can be represented like this. Theta of S upon TM of S. Input is TM. Input is TM of S. Output is theta of S. So if we combine all these together, if you come, one more equation is there. That is for KB. What is EB equal to what? EB equal to KB S theta of S. Now we got how many blocks? How many blocks? For EB, we have to get one more block. EB equal to KB S theta of S. Therefore, what is the output? Output is S theta of S. S theta of S. Input is output is EB. Input is S theta of S. I am deliberately including that S. I'll tell later. EB of S. Output is EB of S. Input is S theta of S. S theta of S equal to KB. Equal to KB. Another transfer function. Another block you got. This block can be represented as KB. Input is S theta of S. Output is EB. If you combine all these blocks together, you will get the representation, block diagram representation of armature control DC. We'll combine all those things together. What is the first block? First block is, this is the first block. First block is, what is output? IA of S. What is the input? EA minus EB. Let us take that first. So we'll take that first. 1 upon LAS plus RA. What is the input given to this? EA minus EB is given as input. What is the output? IAS. Next block must be the input should be IA. If you go there, what is the input IA? Which block has input IA? This block. IA is the input. TM is the output. TM is the output. If you combine that, what you will get is, if you multiply this by KT, simply KT, input is IA, output is TM. Am I correct or not? This is the second block we are going to combine. Now, TM is the input. If you give TM as the input, you will get theta as output. TM as input, theta you will get output. Let us put one S, we will bring that one S here. I am deliberately doing JS square plus BS, you know. In that I am removing one S here. 1 upon JS plus B. Therefore, I can write S theta of S. S theta of S here. Now, this is the third block. This is the third block. Bring that third block there. What is the input? TM is the input. Output is S theta of S. Output is S theta of S. Input is TM. Output is S theta of S. What is the transfer function here? 1 upon JS plus B. Now, one more block we are having. That block is if you give the S theta of S as input, you will get back EMF. You will get back EMF. So we will go there and take this and put that block. That block will give EB as output. What is the transfer function here? KB, that's all. If you multiply by KB, you will get EB. What is the input? S theta of S. So here, what is required here? EA minus EB is required. EA is what? Applied voltage. Applied voltage minus back EMF. So you can put a summing block here. You can put a summing block here. Two signals can be summed, subtract. Op-amp based Summer, subtractor, adder, subtractor is studied. I studied operational amplifier, linear integrated circuits in that. Like that, one summer I am putting. In that summer, I am giving EA as input. EA as input for that summer, and another input is EB, that is in negative sign. So it is a subtractor. That's all. So what you are getting here, EA minus EB. EA minus EB. So EA minus EB is given as input, that will give IA as output. IA is given as input, TM is the output. If TM is given as input, S theta of S, that is velocity, angular velocity, S theta of S. S means what? Differentiation. S means d theta by dt is written as S theta of S. Therefore, S means differentiation. Therefore, this is angular velocity. So that angular velocity is given as input to this block. That gives back EMF. Here, S theta of S is the input. That gives back EMF. That's all. I represented the same mathematical model in block diagram representation. For one equation, one block. One equation, one block. So I got block diagram representation of armature controlled DC motor. Armature controlled DC motor. Now, S theta of S is not the output. Output is what? Theta of S is the output. So what I can do is I can put one integrator here. 1 by S means integrator. You can design integrator in linear integrated circuits. Summer, subtractor, adder, subtractor, integrator, differentiator, you studied. In that, integrator is 1 by S. Integrator. If you put the integrator, S theta of S becomes theta of S. Now, what is the transfer function? Theta of S upon E of S, EA of S. That is the transfer function. So this transfer function we got. This transfer function we got. Transfer function is, each transfer function is represented in terms of block diagram. How we got theta of S upon, EA of S. There I am combining all equations mathematically, and finally I found. Here also you can find. Here also you can find. Here, this is one block. This is second block. This is third block. In frequency domain, all the blocks can be multiplied. All the blocks can be multiplied. Therefore, if I multiply all the blocks together, I'll get KT upon LAS plus RA multiplied by JS plus B. I multiplied all the three blocks together. Now I can get the block diagram like this. I am simplified the block diagram like this. Now I have to remove this feedback, then only I will get the block diagram. For that, the formula is, now you take the formula, we'll see later. Suppose I'm having a transfer function like this, EA of S. Here, this is summer. I'm having a transfer function G. In the feedback, I am having another transfer function H. Here minus, here plus. What is the meaning of this minus? Negative feedback. In amplifier, you have studied that negative feedback only we have to give. We should not give a positive feedback. If you give positive feedback, it becomes oscillator. In oscillator only, it is positive feedback. If it is amplifier, means it should be a negative feedback. In electronics, you studied the same thing here also. So negative feedback. If you have the block diagram like this, if I want to remove this feedback, I want to make this as a single block, means this is equal to G upon 1 plus. If you have a minus sign here, you can write 1 plus. This plus sign is because of this minus sign. Negative feedback means 1 plus GH. So you can find a single block like this. If you apply the same rule there, what is the rule here? What is the rule here? In the numerator, put whatever in the forward path. This is forward path. Am I correct? Forward path. Input to output. You are traveling from input to output. This is the forward path. What is the transfer function in the forward path? That is in the numerator. In the denominator, what is there? 1 plus. Why I put 1 plus? If you have a negative sign, you would put 1 plus. Then in the closed path, this is the closed loop. The closed loop, what are the blocks are there that you put here? That's all. This is the formula. We'll see the formula later. G upon 1 plus GH. That's all. G upon 1 plus GH. If you apply the same formula in the previous block, here you apply the same formula, it becomes, I'll write KT upon LAS plus RA JS plus B whole divided by 1 plus KT KB. Why KT KB? There is one KT, this KB upon LAS plus RA multiplied by JS plus B. In addition, one more block is there that is left out, that is 1 by S. That's all. If you combine these two, this becomes single block. Then cascaded with another block 1 by S, so that can be multiplied. That's all. If you simplify this, whatever you got in the previous mathematically, that you will get the same. Now we have to take LCM. If you take LCM, what you will get is KT upon LAS plus RA multiplied by JS plus B whole divided by 1 plus, therefore, LAS plus RA multiplied by JS plus B plus KT KB whole divided by LAS plus RA multiplied by JS multiplied by JS plus B. So these two getting cancelled. I am taking LCM, that's all. These two getting cancelled. Multiplied by 1 by S. Multiplied by 1 by S. So what you will get here, KT upon LAS plus RA. If you bring that S here, you will get JS square plus BS plus, if you bring that S to this also, KT KBS. This is theta of S upon EA of S. So we got the same what we got in mathematically. You see, compare with this. What we got mathematically, the same transfer function you got KT upon LAS plus RA, JS square plus BS plus KT KBS. You got the same. So theta of S upon EA of S is the transfer function. If you draw for each equation, if you draw a block and the combine like this and simplify the blocks, you will get the transfer function. You will get the transfer function. Therefore, if it is mathematically so difficult, then you can represent each equation by each block and combine them like this graphically. Then you can find the transfer function finally. That is called block diagram reduction technique. That is called block diagram reduction technique. Block diagram reduction technique. Block diagram reduction technique. For that, some set of rules are there. 2 rules we have seen already. 3 blocks are there. If 3 blocks are there, if 3 blocks are there, if 3 blocks are there, the 3 blocks can be multiplied, I said. That is one rule. Another rule, the feedback path can be removed like this, I told you. That is 7th rule. First rule is all blocks can be multiplied. 7th rule is like this, we can, feedback path can be removed. That is 7th rule. Like that, 7 rules are there that we will see in the next class. Then we will take the block diagrams and we will reduce the block diagram into single transfer function. We'll see in the next class.